This means 12 plus 3.
Yeah.
So I will show you my 3 minutes warning after 9 minutes, more or less. Okay.
Yeah.
So you are here, Henk, and also Tim. I don't know if Ricardo is online. So I will sharing the first 3 talks. And I wait, Lindsey say start, and we start. On Bruno.
Okay, in 1 or 2 minutes.
Okay,
I will start the recording now.
Yeah, I see trickling in now. Should I start sharing my screen already, or?
If one, for me, no problem.
Yes, you can. Thank you.
It's okay.
Yeah.
$54. I think we could give it a start now. So welcome everybody to the second day of our Galaxy Cluster Mass meeting, and Lauro will continue the chairing for this first session.
Okay, thank you, Bruno. We continue the discussion about gravitational lensing. The first talk, which is a target talk, is from Henk Hoekstra from Leiden, and you can see the title is Cluster Masses from Weak Lensing. Please, Henk, go, please.
Thanks. That's great to talk about this, and actually it was really nice to sort of see how many talks there are already about weak gravitational lensing. So I thought to focus a bit more on sort of the challenges that we have ahead, and sort of hence is one thing to get a lensing mass from lensing, but I think the real challenge in the future will be how to make sure they're accurate. And there's been some discussion already also yesterday. And so just to repeat, although it's sort of shown last time as well, is why we need masses, right? So there's one thing to find clusters in the universe, but really if we want to use them for cosmology, we need to know how massive they are, because really that makes them special, because they are these peaks in the matter density distribution, of which we can try to measure individual masses, and then by counting clusters as a function of mass and redshift, we can do cosmology. But this plot is already actually quite old, from Planck, where the measurement of sigma 8 in particular is like this extension with the Planck primary CMB, and you can sort of play with sort of what we call the hydrostatic bias. So you can use the SZ signal to get an estimate of the mass, but that is modulo the bias provided by hydrostatic equilibrium, and you can play with the sort of bias that we might expect, and you get different cosmological parameters out. So this is completely degenerate with that, and then you see different colors, different ways of different projects that calibrate the masses. So there's a couple of things here. Is one, there's clearly variation in the results, but also I think perhaps more important, the error bars are still large, and that's really because we're limited by or at least at the time we were limited by the number of clusters for which we had these masses from lensing. So the key is we need masses of clusters, and well, that's, as this picture already shows a complex issue, right? That what do we mean exactly with mass of a cluster? Because clusters are complex structures in a complex environment. And so there's issues about what is part of the cluster, right? Is some part, is it split up in two? How do we deal with that when we compare or contrast it to a cosmological prediction? And even once we decide on that, like, how do we then infer the mass of these complex structures? And so, right, this is sort of sketch the pictures. Also how to find clusters plays a role in here. But regardless of all this complexity, right, the key step is to have a weighing scale, right? So regardless of what we put on this, we need a weighing scale, because otherwise we can't even measure mass, period. And that's really where weak gravitational lensing has become a very prominent tool, especially if I compare to 20 years ago, where, yeah, we were looking at sort of individual systems and things seem to work reasonably well. If I compare to many talks yesterday, and there's more coming, where lensing is starting to become really this prominent tool which we compare things to. And so the one reason is because the measurement of the lensing signal does not involve astrophysics. It's basically uses the fact there's some mass, that mass distorts space-time around it. And we understand, well, if we sort of assume general relativity, we understand how that mass distorts the space-time. And so the only thing that matters is the geometry of that mass distribution. And we can measure this by measuring the shapes of distant galaxies, and they provide then an unbiased estimate of that lensing signal, albeit noisy. So that's what we'll see is always a challenge. So weak lensing mass may be accurate, but it will never be precise, right? It will always have, for an individual cluster, a very large statistical uncertainty. So we can stack things, which has its own complications, but at least it provides us with, at least for ensembles or combinations of clusters, a very well calibrated, or at least an approach that could be well calibrated. So we can measure that lensing signal very well. So what we need for that are, as I said, like we measure the distortion of space-time by the sort of tidal stretching of distant galaxies. So we need very accurate shapes. We need to measure the shapes, these alignments, these apparent alignments in galaxies, correct them for instrumental effects. So we need deep images with good image quality. The other thing is that these, right, because it's a geometrical problem, we need to know when we look at a distant source, we need to know its redshift. So basically its angular diameter distance with respect to the lens. So we need to know the geometry. So we need to know the redshift distributions of the sources very well, or one step further, have individual redshifts for the sources. But with well-calibrated photometric redshift distributions using deep spectroscopic data, we can in principle figure out, okay, we're looking at a particular subset of galaxies. These are their redshift distributions. But then there's a complication, because clusters of galaxies have galaxies in them. And of course, these galaxies distort locally that mean redshift distribution. So we need to account for the fact that there's an excess of galaxies that are not lensed by the cluster because they're part of the cluster itself. So we can account for it statistically by measuring that excess clustering, or by combining with multiband data, get individual redshift for the galaxies. And that way we can get clean samples of sources and really filter out these, in this case, contaminating galaxies. But in principle, we know how to do this. And so we can measure this lensing signal now extremely accurate. Like, we made a lot of progress also improving the shape measurements. And so now, right, in a way, it's also nice to contrast to my thesis, because Ricardo Herbonnet, as part of his thesis, studied 100 clusters. I did 3, so that shows the progress in 20 years. But I would also argue the accuracy, so the level of calibration that has gone into that analysis has improved dramatically. And so this is sort of the summary of that paper, where we compare to Planck SZ measurements and sort of then directly, you can read off this hydrostatic bias on this. It's not quite hydrostatic bias in this case, we're comparing direct to SZ, but we see that, right, we get a value that is not 1, it's significantly off from 1. So there is this bias in the SZ masses. But to reconcile with the Planck measurement to the Planck primary CMB, we would need a value of about 0.6. That is also inconsistent with what we see. And actually, the values we're getting are pretty much in line with what hydro simulations show. And also one thing, actually, was got brought up yesterday as well. So we split by mass and redshift, and we don't see any trends there either. So it's really sort of that bias, at least within our relatively large error bar still. There's no trend with mass and a significant trend with mass and redshift. But we can now do this almost routinely for large samples. And of course, in the next couple of years, this is going to explode with Rubin Observatory and also Euclid. So this is a study we did some time ago, just asking, okay, we need these accurate shapes. Well, when I put on my cosmic shear hat, I have to also measure accurate shapes. So is the design of Euclid sort of out of the box sufficient to measure the lensing signal around clusters? And the answer is pretty much yes. So the gray line here at the bottom is sort of the requirement for cosmic shear. And then we asked, okay, let's take a mass function. Just let's assume we find all the clusters, give them an NFW profile, and measure their stacked lensing masses. You see there's 2 curves here. One includes also the large scale structure noise. So there's basically the stuff along the line of sight, which is random, which increases the noise effectively. And so those are sort of the more realistic ones. So at low redshift, that lowers the signal to noise we get. But basically this shows the signal to noise when we sort of average all possible clusters that would be present in the survey area. And we see that no matter what, these lines are well above sort of the systematics limit that which the mission is designed to achieve. So there's some subtleties, right? Of course, we need to account for the fact at this level that some cluster members, even though we have photometric redshifts, there's an excess chance of an asymmetric chance of cluster members scattering to the source sample. But again, you can model that and correct with this. And the real challenging one, right, this is idealized, is where's the center of a cluster, right, which is tricky. And so that's really the key. So the challenge, I think, for the coming years is not so much the measurement. I would say it's solved, like there's still details that we need to fill in, but we can measure accurate shapes. We do know the source redshift distribution is better than ever and that it's improving, but it's really the accurate interpretation. I think that's where the challenge, because clusters are not spherical cows, right? And there's sort of early work by Becker and Kraftsov, when they look at n-body simulations, right? The clusters are in themselves embedded in a clustered environment. And so when we measure the lensing signal, it's a non-local measurement of the overall mass distribution. So it's also sensitive to the other structures around. And so this shows a deviation with respect to an NFW profile. So on small scales, the halos are the NFW profile, but on large scales, these other contributions need to be accounted for. You can't just fit an NFW profile because you would end up with a biased estimate. And with Stein de Bakker, a PhD student here in Leiden, we went a step further and say, okay, but baryon physics redistributes gas in clusters. And for instance, when we measure when people measure the baryon fraction in clusters, you find that indeed that is a function of cluster mass. We see the impact that lower mass systems, the baryons are partly blown out, move to larger radii, and that changes the density profile. It turns out, and that's on the right here, that if you then fit an NFW profile to the lensing signal that you predict from that redistributed mass, so it's dark matter plus baryons, which are treated separately with the beta model, you get more or less the right mass out. So the mass you would get from lensing is still the correct mass. However, when we do cosmology, we tend to compare to mass functions that are based on dark matter only simulations. And these dark matter only simulations implicitly assume that the baryons trace the dark matter perfectly. And so that's no longer the case. So, and that's a very subtle difference here. So we could measure the lensing masses, and indeed they are the correct lensing masses. But when we then compare them to our halo mass function, the middle plot here shows we're making a mistake, because we're comparing actually to the wrong masses, because the dark matter equivalent mass is not corrected for the redistribution of the baryons. And if you ignored it, for stage 4 surveys, this starts to lead to significant biases in the inferred cosmological parameters. So this is really something we need to start thinking about, like how, so even though these lensing measurements are really, really good, the challenge is how to interpret them in sort of the modern stage. And I think this is, I think in the discussion I brought this up as well. So I don't see how we can't sort of, although there's ways like aperture masses to sort of reduce sensitivity, at the end of the day, what we need to do is we look at observations, infer masses, learn something about the astrophysics, put that into hydro simulations, observe those hydro simulations, and see how, if we can come to a consistent picture from which we can then do galaxy formation, which is, I think, inevitable, and do cosmology. So I think, but at the same time, the data that we're getting will be of tremendous value to really close this loop, because in a way I have a loop here, but in a way that the interaction goes both ways. So I think this is really sort of the next stage, is sort of really getting the details under control by carefully simulating clusters and comparing to the amazing data that is going to come. And so I think to conclude, we can measure accurate cluster masses using gravitational lensing, but we need to account for the complexity of the baryons and the geometry. And I think the way forward is to sort of test the models and then use things like machine learning, which I think we'll hear about tomorrow, to sort of make the links to these multi-observable things to mass. And it's clear that lensing plays an important role in calibrating these relations, but it needs more than just weak gravitational lensing. So thanks.
Okay, thank you, Henk. It's time for question. So I'm looking for your raised hands. So I have my curiosity if no one asks questions. So what is the robustness of your result on baryons on the assumption of the gas astrophysics? Because in the paper, in the plot you showed, there is a comparison with a model for baryons, but we know from simulation that there are some differences in the result for baryons. So what, in your opinion, what is the level of uncertainty due to the assumption on the gas astrophysics?
Yeah, so it's still, well, in the simulations, there's still quite some variation, but I would say also, so this model was a toy model based actually on data. So we used the observed scaling relations, but also there's uncertainty because we don't know what the radial distribution of the gas is. But I would say actually once you fold in, say, look at scaling relations, which some of the hydro simulations predict, sort of if you sort of restrict it to say which ones are consistent with the X-ray scaling relations for clusters or Z scaling relations for clusters and groups, then I think the uncertainty would shrink. So basically, I think that's also really important. And I think it's also really one of the key developments in the hydro simulations, where they're sort of starting to calibrate their subgrid physics to match these observations, which I think is really has revolutionized and really like improved the agreements.
Okay. Another question from Nicholas. Fast, please.
Yeah, Henk, you said, I believe you said if you use just NFW, you can actually do pretty well at the high mass end. Doesn't that sort of go counter to what some other people have found in the past? There's the Lee et al. Paper and the Henson et al. Paper that found sort of like 5 to 10% differences if you fit dark matter only to a full hydrosim.
Yeah, but then you change the probe. So basically what we're getting the right mass, but the wrong profile, right? So you can't interpret the signal as to turns out that overall it still looks like an NFW profile, but the concentration is off. And we did find that, so when you leave the concentration free, you can sort of compensate for the differences. But it also very important is the radial range that you use in the fit, right? It's also what Beck and Kraftsov really showed. The moment you go too far out, things really start breaking down. So yeah, you have to restrict the range. So that's what we did. We used pretty much what we used in observations. So it's a mix of things. So you have to think, what radial range do I use? And then actually there's less sensitivity to this. But the point is that really you're misinterpreting, you're getting the right mass, but when you say what's the scale radius, you get the wrong answer. But it's sort of to first order lensing measures mass in this case. And it holds.
Gus, your question is urgent? Or if it's urgent, please go, please.
I think we have time, because unfortunately, I think the next speaker is not available.
Okay. So this is good. So Gus, please go with your question, please.
Thank you, Laura. And hi, everyone. Henk, really nice review of what's going on in the lensing world. One issue that, and I love your plot of the circle, the virtuous circle that involves taking data, but also producing data through simulations. And my question for you is, we have various simulation groups capable of making very sophisticated hydro treatments. How do we move forward to bring some collective understanding of what the theoretical signal is, and address the sort of theoretical error bar in all of these predictions?
Yeah, so I think that is the challenge, because well, I'm fortunate to be in a place with some simulators which we can directly collaborate with, because it's also observing the simulation, really generating the images, and then really interact with the observers to make it look the same way, because the simulations are now getting so good that if you're not careful there, you draw the wrong conclusion. And so I think I think it would be great to have sort of a reference set. Like, as I said, at some point there was a lot of discussion, the AGN feedback for cosmic shear, like half these models, they are excluded by scaling relations. So really, should we plot these lines on the figures or not, right? So I think and in a way it forces everybody to sort of think of that circle, that we should not be thinking of things in isolation anymore. So it's the scaling relations is relevant for cosmic shear, which then by itself is important for clustering of 3 times 2 points. So so we still talk about cosmological probe, but I'm more and more that it has to be this very concerted effort where everybody pitches in.
Okay. I stop here the discussion also because at the end of the day, there will be a discussion about these things. So please take your comments and suggestions for the discussion at the end of the day. The following speaker arrived, so no problem in the program. So
okay.
This is good. So the next talk will be by Ricardo Herbonnet from the Stony Brook University. And the talk is about the brightest cluster galaxies trace weak lensing mass bias and halo triaxiality. So please, Ricardo, you can share the screen.
All right. Sorry for being a little late.
No problem. Okay.
Go.
I will give you a warning when 3 minutes are left.
Yes. All right. This is a talk about a project that just came on the archive this morning, which I did with Adrian Crawford and Camille Anstrus and the 300 collaboration. And it's about how can we use more optical data to improve our weak lensing masses. So we have these beautiful images of halos from simulations, and they look something like this from the Millennium simulation, and they're clearly triaxial things. Whereas as a weak lenser, I look at it and say, well, on average, that's pretty round. And for instance, this study by Massimo Viola shows that if you take enough clusters, yes, yes, clusters on average look round. But that ignores the fact that for individual clusters, your masses might be very much off because you're assuming a spherically symmetric model for something that clearly isn't spherically symmetric. So that's, for instance, this plot from Osato in 2018 shows that you can have a 20% scatter by using these spherically symmetric models, depending on the inclination of the halo. If you look at it along the line of sight, you're going to overestimate your weak lensing mass, and vice versa, you're going to underestimate your weak lensing mass if it's in the plane of the sky. Even worse, you can also have selection bias, because as weak lensers, we think in averages, and we think on average clusters are round. But if you select clusters based on their orientation, you're not going to get an on average round sample. You can get a selection bias in your cosmology, and you're not going to get the right cosmology out of it. So we were thinking, can we do something with just the data that we have in hand and improve this? Well, we know that baryonic material follows dark matter distribution, and specifically the central galaxy, which we call the brightest cluster galaxy, because it's usually the brightest, should be aligned with its host halo. In this figure from Ragon Figuera, it shows that, yes, the BCG is on average aligned with its host halo. It's not just this simulation, but it's seen in many, many other simulations. So we think this is probably a fundamental thing in the universe. And the great thing is that BCG information is already there in the lensing surveys. This RadMapper always decides upon what is the BCG because they need a center of the cluster. So this information is already in hand. Can we use it? Well, so what do we know about BCGs? Well, they're prolate spheroids, so ellipsoidal things. And what does it tell us? Well, here's a simple sketch. If you look at it from different orientations, you're going to see either a rounder BCG or a more elliptical BCG, depending on what you're looking at. So if your BCG is oriented along the line of sight, the projected BCG looks round, and vice versa, if it's oriented in the plane of sky, it'll look elliptical. So in summary, the BCG shape is a proxy for how it's oriented towards us. The BCG is aligned with halo, so the BCG shape is a proxy for halo orientation, and halo orientation gives a bias in your weak lensing mass. So can we use this information? I looked at this with 50 clusters from the Weighing the Giants program, very, very massive clusters. And we looked at the scatter in the weak lensing mass, where the true mass was derived from the gas mass. Shapes of BCGs were measured with GalFit. And yes, on average, we saw that our hypothesis was correct, that rounder BCGs have on average higher host halo weak lensing masses compared to what we think it should be from gas mass. This is in agreement with what other people also found, like Dan Morone, Andy Medavi, and Daniel Grun. So we think that this might be a good way forward. Next step is to see, can we verify this in simulations? Great thing about simulations is you have 3D information, but you can also have projected information. There's weak lensing masses by Carlo Giopoli, and you can look at different redshifts to see if what we found in data actually evolves through time. The 300 project is great because, like it says, it has 300 clusters, so lots of data for us to work with. So in 3D, just a quick method section. We measure using the moments of the mass distribution. This should probably be fairly straightforward for most of you. The halo shapes were already calculated by Alexander Kneve, and we calculate the 3D shapes of BCG ourselves with a unweighted or radial top hat. And we look at different radii of the BCG to see does our alignment change with the BCG assumed edge. Secondly, there's also an indication that relaxed clusters might show more alignment between the BCG and the halo. And since there's not a clear definition of relaxed, because it's a sliding scale, we use two different definitions of relaxed in the simulations just to see whether that made any difference for our hypothesis. So the results, not surprising, we find what other people also find is that the alignment between the halo and the BCG, it's there. They're preferentially aligned with roughly 18 degrees between the two major axes. We also see that, as we expected, relaxed halos, according to the Sway criteria, so the more strict relaxed criteria, they're more aligned with their BCGs. So what does that mean? Well, here's another thing that most people already knew. If you look at the weak lensing mass scatter, so the weak lensing mass divided by the true mass of the halo, depending on the orientation, you're going to get an over or an underestimated weak lensing mass, like I showed you in the beginning. So by 20% or under or overestimated, depending on the orientation of the halo. Now, if we combine these two plots, we get to the plot on the bottom right. The BCG orientation with respect to our line of sight correlates with the weak lensing mass scatter. So if we knew the orientation of the BCG, we could hopefully predict the weak lensing mass bias for individual clusters on average. We could correct our weak lensing masses using the BCG orientation. This is all 3D. It's great. That's what simulations give us. But as an observer, I can't access that data. So let's go to 2D instead, which is what observers can see.
3 minutes.
Sorry, 2?
3 minutes. 3.
3. Okay, that's good enough. So we measured shapes of the projected BCGs and basically redid the same analysis, see if it correlates with the weak lensing mass scatter. If you're interested, we use different shape measurement algorithms just to be extra careful. And this is the main result. If we go, let's focus on the picture on the right first, that the measured shape of the BCG is an indicator of your weak lensing mass scatter on the y-axis here. The bluer bands show more relaxed clusters. So again, relaxed clusters have this relation more clearly than the full population. And just and we see that going further out in the BCG, so towards the intercluster light, this correlation increases, correlation strength increases. Finally, quickly, there's another orientation proxy for the BCG, which is the concentration, so how much light is concentrated in the center compared to the total outer mass. So here's another sketch of that. So the color here indicates density along the line of sight. So if you're looking towards your BCG along its major axis, there's going to be more mass concentrated along the line of sight, naturally, because there's just more matter there. So this means that if you're looking along the major axis, you're going to see more matter projected in the central region, whereas if your BCG is oriented in the plane of the sky, you're going to see less or fewer matter, less matter projected in its central region. Just in the last minute, we also checked this out. That is the plot on the left. See if there is a relation between the concentration of BCG mass in its center compared to its outskirts. And we don't see anything with the scatter and weak lensing mass. What we did see is we verified what Song Huang found, is that this concentration of mass of the BCG is a good indicator of true halo mass. So we think this might be a useful tool to help increase the precision of weak lensing masses. And just for summary, the main problem is weak lensing cluster masses. They're biased due to the orientation of halos. Our main assumption, which has been verified by many simulations, so we think this is a pretty fundamental thing and not a fluke of a single simulation setup, so BCGs are aligned with their halos. And then our next step was just use geometry to find proxies for BCG orientation and hopefully increase the precision of weak lensing cluster mass estimates. Thank you.
Okay, thank you, Ricardo. It's time for question to Ricardo. I see Andrea, please.
Oh, thanks for the nice talk. I just wondering, when the BCG is not well defined, imagine a cluster like the coma cluster. It would still be perhaps a possibility to use the overall galaxy distribution to infer something about the shape of the cluster. Would it be? Have you tried that?
We haven't tried it for this project. That's going to be the next step. So yes, there's the obvious downfall here that BCG isn't always perfectly determined. RedMapper has, I don't know, 30% maybe uncertainty on the BCG determination. And the next step is, of course, if we increase the number of galaxies we look at. For this one, it was just the main draw of this method is that it's fairly simple. You just use geometry of the BCG. So we thought that was physically intuitive.
Okay, there is a second question by Zhuan Zhang.
Hi, Ricardo. It's a really nice talk. I was wondering what physical scale you use to measure the shape of the BCGs. I read, I think it was from Steve Allen's review paper, that because of the Surzic profile, that depending on where you cut off the shape, where you cut off the profiles, the galaxies, their shape and orientation could differ. Like it could be rounder if you use more smaller radial profiles. So have you ever considered that factor in the shape measurements?
Yes, excellent question. The short answer is you're absolutely right, and we can talk offline about the details. But so what we did was we measured the ellipticity at different radii using this contour. So just draw an isofocal contour that gives you the shape at different radii. We then found that if you go from 50 kpc to 100, you get a better correlation between the BCG and weak lensing mass. Is that
okay? Yeah. Thank you.
Thanks.
Okay, sorry, we are running. Please, Wonky, please put your question on the chat, and Ricardo will answer. But we have to move to the next talk. Sorry, because if not, we are. Thank you, Ricardo. We move to the next talk. It is by Tim Schrabback from Bonn, and the talk is about the constraints and mass scale of distant SPT cluster for cosmology using HST weak lensing measurement. Tim, please go, please.
Okay, hi. Can you see the slides?
Yes.
Okay, great. Yeah, so thank you very much to the organizers for organizing this excellent meeting and for giving me the chance to talk here on behalf of the South Pole Telescope collaboration on our efforts to use Hubble for weak lensing mass measurements of high Z clusters. So what I show you will all be based on the SPT asset cluster sample, which will be introduced, I think, in much more detail in the following talk by Lindsey Bleem. So let me just say this is a 2,500 square degree survey conducted by the South Pole Telescope, and it found clusters via the Srinivasan effect. For the purpose of this talk, we have the cluster sample here as a function of redshift, and then you have the detection significance in the asset, which is viewed as a good proxy for the cluster mass. But of course, if we want to use this kind of cluster sample for cosmology, we have to calibrate the absolute mass scale using weak lensing. And it's not only the absolute mass scale, but also its redshift evolution. Why is that important? You can look at this figure here from a paper by Sebastian Bocquet from the latest cosmology results. You see that, for example, your equation of state parameters of dark energy are pretty degenerate here with the term ZS set, which is the redshift evolution in the scaling relation. So if you want to constrain this or other properties regarding the growth in the cluster population, you really need to constrain the mass scale as a function of redshift. And in SPT, we've been doing this by adding both lensing data at low and at high redshift. The previous low redshift work was based on Magellan data led by Jürgen Dietrich. Sebastian Bocquet will later today give an update on ongoing work using the dark energy survey, for example, to improve the constraints at lower redshifts. At high redshifts, we've been so far using Hubble. And of course, Hubble has the advantage that it gives very deep and high resolution images, which you can use to resolve the shapes of the small and faint galaxies in the distant background, right? Because if you have a cluster at redshift 1, you want sources at redshift 1.5 or 2, which tend to be really small and faint. So in practice, what do we need to do for this? Well, we need HST images. We have to select our background population using photometry. We have to calibrate the source redshift distribution. We need calibrated shape estimates, and then derive our mass constraints. And I will briefly take you through these steps on the following slides. So let's start with the data. So this is all for clusters with a median redshift around 0.9. We had a first sample published in this paper, which were 13 clusters, for which we had HST ACS mosaics, which are really nice because they probe the cluster lensing out to the virial radius to get good mass constraints. So for example, you can see this nice cluster here. We've recently updated this, applying some updated calibrations. We added deeper photometry for some of the clusters for the source selection, and we also expanded the sample to a total of 30 clusters. But most of the new clusters only have single pointing data, so they don't give us the full coverage and only probe the inner regions of the clusters. Oh, sorry, we should not arrive here. Somehow it jumped ahead. Yeah, okay. So then we need to select our background source population. For this, we add I-band photometry. We already have V from HST, and then we add I-band. If we had many bands, we could get deep photometric redshifts, but for this, we don't have enough coverage. But with just 2 bands, actually, we can do pretty well, which you can see in this figure here, showing you these data from the candle survey for galaxies here, the photometric redshifts versus the V minus I color. And our clusters are at redshift 0.6 to about 1. And you can see if we select blue galaxies in this color, we actually remove the cluster galaxies extremely effective, like both blue cluster galaxies and red ones, which would live here. So we don't have to worry about the cluster member contamination, which is something which Henk mentioned before with this kind of selection. And we actually select most of the background population, which carries the lensing signal way above redshift 1. So that's very nice. You do get a bit of a foreground contamination, so that's something you have to know quite well in order to interpret your measurements accurately. So this brings me to the calibration of the source redshift distribution. We use the data to approximately 26.5 as a V-band magnitude, which is for HST fairly shallow, but compared to the ground-based data, which are used for weak lensing, this is really deep. So of course, if you want to calibrate your source redshift distribution, this is a bit more tricky because you need fainter calibration samples. For this, we've mostly been using the candle survey. which is good because it gives sufficient depth in coverage and has already enough area on the sky that sampling variance is not an issue. But of course, if you calibrate against photometric redshifts, you have to make sure that those are actually good enough and well calibrated. And we've investigated this, for example, through comparison to much deeper data from the Hubble Ultra Deep Field or also very deep spectroscopy. And if you do this, then you find that this particular set of photosys which we used actually does suffer from issues. In particular here, if you compare, this is the photometric redshifts in the 3D HST candles catalog, and this is the deeper redshift estimate based on the ultra deep field. You see many galaxies are on the 1-to-1 line, but you have these catastrophic redshift outliers here, okay, which is basically the candles catalogs tells us they should be a low Z, but actually they seem to be at high redshift, which of course for lensing makes a big difference in the lensing efficiency. So that's something we need to correct for. And we believe that we have this under control to about the 3% level at the moment, which is fine for current data sets. But if you think about future programs, of course, you want to do better. And by the way, there's a paper from Fatima Raihan who has looked into this in much more detail, investigated this issue, what's causing these outliers. So if you're interested in the subject, I recommend you to look at that paper. Another issue are shape measurements. Here we use an updated calibration from Beatrice Hernandez Martin, which she recently did as part of her PhD work. And I mean, this is like the usual weak lensing calibrations where you generate image simulations and then see what shear you recover. But one of the additional things she's been doing here is really looking at cluster-specific issues such as stronger shears or increased blending, which you get if you add your cluster population in front of your background. And what you find there is that this affects your shear calibration at the percent level. Okay, so again, for current data sets, that's not really an issue. But if we think about Euclid and future programs, it's really something which you want to take into account. So you want to have basically a cluster-specific shape calibration. Final thing to do are the mass constraints. So as we've seen in previous talks, we have, for example, here for this cluster, our tangential profile of the reduced shear, which you can fit with a model like an NFW, where we cut out the core because that's where you're most susceptible to systematics. This is the corresponding mass reconstruction. But as we also heard from Henk's talk, for example, these fits do not have to be exactly unbiased. So what we do is we then calibrate these measurements on simulations where we perform exactly the same kind of measurement. And this is from a recent paper from Martin Sommer on the subject, which, for example, shows to you that he has a function of the true mass of a halo in the simulation, in this case, the MXXL simulation. How does your recovered bias in the weak lensing mass depend, for example, on the mass concentration relation that you assume, right? So there's obviously a dependence, so you really need to account for this. And then there are more effects such as miscentering, which is something which Henk also mentioned. We don't really know where the true halo center is on the sky, so we have to use, for example, the X-ray or the asset center as a proxy, which then also affects your masses, and you have to calibrate this on the simulations. Let me just show you some results from the recent paper. So the details on the SPT asset cluster scaling relation and cosmology pipeline will be explained in Sebastian Bocquet's paper. So let me, his talk, his upcoming talk today. So let me be very brief. Up here, we can see basically a summary of the results. On the x-axis, we have the mass inferred from the lensing data corrected for these mass modeling biases. And then on the y-axis, we see the debiased SPT detection significance, and then this extra term here, which comes from the redshift evolution term. So this has been taken out here. And then you can, I mean, you see the data are very noisy, the individual lensing masses, but as long as all the scatter is accounted for in the analysis, that's fine, and you can calibrate the overall normalization of the relation. Okay, and this is also shown here. Now as a function of redshift, you see basically this is the result of the scaling relation analysis at a reference mass, which is close to the median mass of the sample. What set detection significance do you infer? Okay, and the blue band basically is what the lensing data tells us. The higher up this is, the less massive the cluster population. Thank you. The further down, the more massive it is. And you can, for example, see that, yeah, the clusters are less massive than what you would, for example, see in this gray band here, which is what you would expect from Planck in the lambda CDM cosmology, given the SPT cluster count. So this is basically equivalent to the observations that clusters give you lower sigma rate than Planck, but now in terms of scaling relation. Just very briefly, what is next? Fairly soon, there should be a paper led from Hannah Zoren, and she analyzed a sample of 9 further SPT clusters at even higher redshifts. There's even more tricky to select the background population. So she did this here by adding HSTJ band and VLTU band, in fact, which works quite well to select your redshift 2 and above background population. But also here you get some foreground contamination, and this paper should appear in well, several weeks timescale. Just as a final thing, let me add a few thoughts maybe regarding the things that we should do in preparation of the analysis of the stage 4 lensing surveys, which will give us much better statistical precision, basically relating to some of the points Henk mentioned. Some things we should work on. So we do want this cluster regime specific shape calibrations. A very important issue, I think, are the mass modeling corrections. Henk already mentioned the impact of baryons on the density profiles. And one way to solve this is, for example, suggested in this paper by Sebastian Grandis, that you could analyze basically with the same initial conditions, dark matter only simulations and hydro simulations, use the hydro simulations to derive your mass modeling biases for the lensing data, but use the corresponding dark matter only mass function predictions to link the cosmology accurately. And similarly, we need to work on improving our understanding of the miscentering. You can do this with hydro simulations, but I think we really want to use some cross-checks within the data to see how accurate this is. For example, you can look at how well the lensing signal is modeled at small scales. Final remarks on the high redshift clusters. Here, one thing to notice that the statistical errors increase very quickly with redshift. So you can think about maybe some optimized trade-offs in terms of systematics there, which maybe you can push the data a bit more compared to what you would do in cosmic shear. The calibration of the redshift calibration is tricky here because we're still lacking spectroscopic redshifts for some of the high redshift galaxies. And then I mentioned this issue of the redshift outliers. That can be tricky to calibrate, but one way to solve this is to use data which are actually near-infrared selected, like in the H band or the K band, which, for example, you should be able to do with Euclid and Roman pretty well. Okay, let me just put up my summary, and thank you for your attention.
Okay, thank you, Tim. So there is time for question to Tim. So Andrea again, please.
Hi, Tim. Very nice talk. I was just wondering, it's not specifically related to your talk, perhaps I should keep that for discussion, but rather than using simulated clusters, there are now clusters for which we know, the weak lensing is so accurate, the masses are so accurate, all the reconstruction is so perfect that one could think of using the frontier field clusters and degrade the signal in such a way to simulate what you expect in these more general, shallow surveys. Would that be an option to?
Yeah, the problem I see there is that these are, of course, not fully representative for the clusters we want to study, right? I mean, if you talk about redshift above 1 clusters, which were selected in a different way, their properties in terms of density profiles may be different compared to the really well-studied clusters at lower redshifts. Okay, so I mean, I think the well-studied clusters are really useful to cross-check, for example, your hydro simulations. But then I think you do need the simulations to extend this to different cluster populations.
Thank you.
But maybe let's discuss this offline in more detail.
Other question to Tim? If not, let me thank Tim and all the other speakers of today. I leave the chair. The new chairperson will be Barbara, because we are moving to SZ from now. Thank you very much. Barbara, you are?
Yeah, I'm here. So welcome to the section on galaxy cluster masses derived from SZ. So we have 4 talks in this section. So I remind you that I will show this when you have just 3 minutes left. So let me know in some way that you have seen it, otherwise I will tell you. So we begin our section with a review talk by Lindsey Bleem from the Aragon National Laboratory on the recent progress in the SZ cluster cosmology. So please, Lindsey. if you can share your screen. You have 20 minutes plus 5 minutes for the questions, so please.
Okay, is this working?
Yep.
Perfect. Okay, thank you. And I'd like to thank the organizers for inviting me to talk at this really interesting conference. So as Barbara said, today I'll be telling you about some rigorous recent progress in SC cluster cosmology. And since this is a review talk, I thought I'd put a little bit of review right at the beginning and just say that I'll be really focusing on abundance cluster cosmology. So what we can learn by counting the abundance of massive clusters as a function of redshift, because of course this can explore a whole suite of really interesting cosmological models as illustrated by these curves extracted from a suite of cosmological simulations run by my colleagues at Argonne. Now we've heard yesterday quite a bit about some optical clusters, and we'll hear more about later about X-ray. I just wanted to put SC into context here. And this is a bit of an older figure, but I think it really illustrates the point of where the advantages of SC surveys come in. So we're plotting the redshift versus the limiting mass, or approximately the 90% completeness of each of these surveys. And I do want to say one can quibble about 90% completeness because, of course, this depends on the signal to noise of the cluster or the counts in the X-ray or the richness in the galaxies. But what it really illustrates when I want to talk about progress in the SC surveys is the tremendous progress we've had over the last decade with millimeter wave sky surveys. There's been about an order of magnitude sensitivity approximately every grad school timeline. So we've had really tremendous upgrades, especially in the ground-based surveys. I will say that my talk, what happened here, is going to be a bit biased since I work on the South Pole telescopes. My results will lean a bit more towards SPT, though of course we'll hear later in this conference from, for example, Nick Battaglia and other people working on ACT and Planck. So the SC effect is by now very well known, but just to remind you, what we're observing is the 1% of CMB photons, the inverse Compton scatter off the Haupt gas in X-ray clusters. This causes a distortion to the 2.73 Kelvin CMB black body and results, when you look in the sky, at a decrement below frequencies of 220 gigahertz approximately, and an increment above on cluster size scales. So particularly for high redshift clusters, these are roughly in arc-minute size scales. One really powerful thing about clusters is because we're probing the thermal energy of the clusters. Simulations and now observations have shown that this SC observable is really tightly correlated with cluster mass. So we have a tool in which we can select a redshift independent cluster sample, which is a really good mass proxy, and currently just limited by the sensitivity and frequency coverage in the future of our instruments. Now, to detect these subtle distortions on the cosmic microwave background, these are a few hundred at most microkelvin fluctuations typically on arc-minute scales. We really require high resolution, wide area cluster surveys to blindly detect these clusters. There are, of course, a lot of really nice follow-up instruments, but I won't be focusing so much on those on these talks. In particular, I'll be highlighting results from ACT, SPT, and Planck, where the recent progress and the future progress in the field is going to be primarily driven by the ground-based surveys, where there are, of course, trade-offs. Planck is all sky, can really do this wonderful multi-frequency coverage of the sky. But on the ground, we're limited by our atmospheric transmission to a few frequency windows. And I'm just illustrating for you what windows we're probing with SPT versus the water breaker that we always fight. So we observe at 3 frequencies with the South Pole telescope, 2 probing the SC decrement, 1 probing the null, and ACT and others have observed in the increment as well at a bit higher frequencies. Now, just to give you a flavor for what the data we take on the sky actually looks like. So of course, this is WMAP in a 50 square degree patch. Planck completely revolutionized our view, especially at higher angular resolution and much more sensitive. So this is the same 50 square degree patch observed by Planck. And then we hit the ground-based telescopes where you can really put large apertures. We can't launch it to space, which really give you high angular resolution, as well as the ability to spend years drilling down on a deeper patch. So this is an example from the recent SPT pole survey of that same 50 square degree patch of sky. where you can really see the benefits of a 10-meter aperture on the screen. Now our map noise, if you lightly filter that to remove the largest scales, is primarily dominated by CIV anisotropies in the cosmic infrared background. There's quite a lot of bright emissive sources, so AGN and dusty star-forming galaxies. And at this particular frequency, 150, we're in the decrement of the SE effect. So you can see these shadows are clusters of galaxies. We use all the information encoded in these maps to optimally extract the SC clusters using multi-frequency match filter techniques. And this older paper by Milan is a great illustration of this, or explanation of this, where we can combine the different sources of noise, for us, the primary CMB, the CIV, as well as information about the angular extent of our clusters to optimally extract the cluster signal and find these clusters. So from the first detection, which just happened a little over a decade ago, we now have over 4,000 massive clusters discovered blindly in SC surveys from Planck and ACT and SVT. Now, because the SC effect is redshift independent, SC cluster cosmology is really a marriage between the optical infrared cluster communities and the SC cluster community, both to confirm the redshifts of these clusters by detecting galaxy overdensities over either photometrically or spectroscopically, or as you just heard in the nice talks in the weak lensing, especially by Tim for the SPT sample, using these to provide direct mass calibration via weak lensing. And with that information together, we can then put the SC surveys onto the typical mass redshift diagram. And this really illustrates the power of SC surveys to detect massive clusters out to the highest redshifts which they have formed. Now for the next few slides, I'll be focusing on recent results from the SBT cluster sample. And I just wanted to highlight a recent work by graduate student Nicholas Wong, who led the first cluster analyses of the SPT 400D data, in which we're really pushing down, using that new instrumental sensitivity, the mass thresholds of the SVT survey, of the SC surveys. So now that we've collected our cluster sample, we do, of course, focus on cosmology. And we've been using the same sort of philosophy for almost the last decade with the South Pole Telescope, in which you use Monte Carlo Markov chain techniques to simultaneously fit for cluster cosmology and cluster mass observable relations in a simultaneous and self-consistent way. Where we use the typical cluster scaling relation parameters involving a normalization, slope, redshift evolution, scatter, and particularly for follow-up observables such as the X-ray of the weak lensing correlated scatter, while we constrain our cosmological models, primarily focusing at this point on lambda CDM, but then some interesting extensions. Now in the talk, a couple talks from now, Sebastian Bocquet is going to tell you in great detail about our most recent results, which we're very proud of. These are what we call our first internal weak lensing cosmology results from the South Pole Telescope, where these are making use of the weak lensing analyses that Tim just talked about, particularly from the Magellan Megacam and the HST data directly on the SPT cluster samples. And what we're finding is that our survey results shown in the left in the omega matter sigma 8 plane are generally consistent with other cluster cosmology programs, such as Weighing the Giants, as well as large-scale structure surveys. At this point, this was DS year 1, still true with DS year 3, and cosmic shear surveys like KIDS and Gamma and then Planck. Now, everything when you stress test it, of course, if you're on the edge, shows interesting, come on slides, polls as we test the internal consistency of the data sets. And this is just one slice. These are what one might call 2 sigma curiosities, whereas we break our cluster sample apart, dividing by mass or redshift, we start to see interesting polls in our cosmological and scaling relation parameters. I'll leave Sebastian to tell you more about this, but this is really both exciting that we're potentially finding new things, worrying we're detecting, the first hints of systematics, or it could be the hints of statistical fluctuations. And so the next steps to really push on this and improve our cosmological constraints are, as you heard from Tim, lensing, and more lensing with DES, Megacam, and the Hubble Space Telescope. And then to grow our sample, we have 5,200 square degrees so far, surveyed by the SPT, 4,700 of which is in the footprint of the dark energy survey. So as we increase our cluster sample, we're only constraining our lensing power, particularly for DES weak lensing calibration. That's going to be coming up this year. I'm going to commit to the 500D SPT full sample coming out this fall. And Sebastian's going to tell you about the cosmology we're going to be doing with this using weak lensing calibrations. So this will be the full pre-SPT 3G sample, including SPT-SC, SPT-ECS, and this SPT full sample, which is 5 microkelvin arc minute at 150 gigahertz, which is 4 times deeper than our previous results from SPT-SC. So really pushing down that mass threshold with these surveys. Similarly with lensing, CMB both provides us with clusters, but it's also a really powerful tool, potentially powerful tool, to actually constrain the masses of these clusters via the subtle distortions the clusters put into the paths of CMB photons. This was really nicely illustrated, I think, in a recent result on the Planck galaxy cluster sample using temperature-based lensing, showing the 1 minus V parameter one can extract using the CMB itself to calibrate the masses of the Planck cluster sample through a combined analysis of the sample itself. And then our next talk, we'll be hearing from Srinivasan Raghunathan about what I'm very excited about is the future of CMB lensing. So this was a recent result, which was the first detection using polarization-based CMB lensing to constrain the masses of clusters. Now this was, of course, a few sigma detection, but we're sort of in the regime where we're going from first detections to robust signals to really cutting edge calibration. And that's where we're going with CMB polarization, which should be the way we calibrate clusters with next generation CMB surveys. And I'll leave it to Srini to tell you the benefits there. Now, I just wanted to bring up another area of focus that's been undertaken with SC cluster surveys. And that's the fact that when we partner with our optical surveys, we really get a beautiful multi-wavelength view of the galaxy clusters we're detecting. And as we know, this is now an old plot, but I really like how it illustrates the power of this multi-wavelength analysis. When you combine optical cluster surveys with SC, you can get an independent cross-check of your mass calibration of your cosmology. And we often find interesting things when we open the box. So this was an example on the max BCG plus optical cluster sample from Sloan, which was studied by a stacked SC measurements from Planck, finding different expectations between the expectations and what the model was for the weak lensing, which spurred a whole flurry of analyses to explain it. And I want to say that we're still, as we push and open the box, we're still finding these interesting tensions between SC and optical surveys. So this is a recent result I led where we took the 4,700 square degrees of SC data and matched it to the optically selected cluster sample from the dark energy survey. On the left, we're showing the richness of the optical galaxies versus a scaled SC signal to noise for the 400 or so clusters in common. And when we combine that with analysis of the SC abundance, now for a fixed cosmology in this case, what we can find is that there is a significant tension in the inferred mass richness relation of clusters derived using an SC sample as compared to, for example, stacked optical weak lensing or CMB lensing. And this 4 sigma tension, of course, can have profound impacts on the cosmology inferred from the sample. We heard a little bit about this yesterday. But I think this was really nicely analyzed in a recent work by Matteo Constanzi, where this plot on the right is now comparing the cosmology from the dark energy survey number counts with optical weak lensing, and that where instead you analyze those number counts, making use of the mass scaling relation you derive with the SC follow-up effectively of the DS red mapper sample, showing much better consistency with both cosmic shear surveys and Planck. One other thing that I think I'm very excited about in the coming years, with this tremendous increase in the sensitivity of the SC surveys, we're really going to be able to directly probe into the heart of what's going on with these scaling relations. So for the 2020 analysis, we had a median richness of the match sample between the SC SPT samples and RedMapper around 60, which was quite high mass, of course. But with the currently ongoing SPT3G survey, where we're more than halfway through our survey, the expected median richness of that match sample, I'm illustrated here, is very well aligned with the median richness for RedMapper, and of course will match well with LSST in the future, especially going to higher, which will push to higher redshift. So there's going to be tremendous capabilities to understand some of the issues we talked about yesterday, such as projection effects, and other systematics in optical and SC surveys moving forward. I just wanted to sort of conclude by pointing out that we not only produce cluster catalogs with these CMB surveys, but the multi-frequency CMB data can be combined to isolate cluster signals anywhere in our maps. This is illustrated here in a recent work I led, showing the combination of Planck and South Pole Telescope SPT-SC survey data, where we really leverage that multi-frequency data from Planck at the largest scales, or low L, and combine it with the resolution you gain from the high L ground-based surveys. Matt Matacharo et al. Also led a recent result on this on ACT for a very similar analysis. And what this allows us to do is on the right, just showing an illustration of a very low redshift cluster, what that resolution can provide, radio source information, as well as very accurate cluster profile information on arc-minute scales. But you can also not only just analyze the big low redshift clusters, but in a really nice analysis by Emmanuel Sean, and I'm sure we'll have more about these things from Nick Battaglia, the ACT collaboration has been focusing on stack studies of galaxies and groups and clusters, and just illustrating the impact of those in the left panel for the CMAS galaxy, showing both the thermal SC and the kinetic SC profiles. So this is really going to become an industry with our sensitive maps going forward. So what's next? I hope I've given you a feeling of this throughout the entire talk, but we've had tremendous increases in the sensitivity of CMB focal planes over the past 2 decades, going from order 1,000 detectors to now SPT3G has 13,000 detectors operating on sky and multi-frequencies with polarization and sensitivity. In the next few years, the Simons Observatory will come online. And finally, late in this decade, we'll have the sort of penultimate ground-based experiment, the CMB S4 experiment, which should put 100,000 detectors on sky, which would be fantastic for cluster cosmology. With these new cluster machines, we're going to, as I mentioned before, see tremendous increase in the number of clusters, as well as the cosmological sensitivity of these clusters. So in the left panel, I'm showing you forecasts for what you should be expecting in the next few years to come out of the SPT3G cluster sample, really pushing our mass threshold down to about 10 to the 14. With the CMB lensing itself, Srini is going to tell you a little bit more about this, but we'll actually be able to get really nice mass calibration of our clusters, particularly at high redshifts, above redshift 1, where it's so challenging to get good mass calibration. This will translate into really tight cosmological constraints, particularly in combination with the weak lensing constraints we're expecting from the LSST. Similarly, from CMB stage 4, we're going to expect over 70,000 clusters. So just really tremendous capabilities should be coming online in the 2030s to complement other facilities. So I'll end here and just say that we've found thousands of these massive clusters reaching out to redshift 1.9, really illustrating the power of these SC samples. These clean mass-limited samples have led to fantastic samples for cosmological and astrophysical studies. And this multi-wavelength survey data is critical for understanding systematics that are going to creep into our cosmological, or already have crept into our cosmological analysis. I'll say the future is bright. SPT3G survey is well underway. We have thousands of cluster candidates. We're actually following up some next week for the highest redshift systems. And CMBS4 is well in the planning stages. And we're going to survey 70% of the sky, leading to detections of over 70,000 SC clusters. Thank you.
So thank you for a very interesting review. So if there is any question, comments, yeah, go Ben.
Hi, thanks, Lindsay. That was really interesting. I was just trying to do the maths in my head, but I'm too slow. So could you say something about when confusion is going to become a problem when we're detecting so many clusters at low masses? They're all going to start overlapping, right?
Right. So right now we're okay. So for SPT3G, we're getting something like 1 cluster per square degree on the sky. So that's going to be okay, maybe a few. But that is a real problem, and especially thinking potentially in the future of CMBS4. And Gil Holder and others actually wrote some really interesting papers about this back when sigma 8 was thought to be 1. This was a real concern for the first SC surveys. But I think that's going to be more of a problem potentially for stage 4 moving forward, not so much in this era. We do have a few cases at this point with our projections along the line of sight, but we're not encountering that so much right now. And I think the optical surveys are going to be a great help for disentangling this in the sense that they will provide, multiple line of sight galaxy overdensities as well.
It'll make the mass reconstruction more challenging, won't it?
Yes, yes, it will.
To work out how much of the signal to assign to the different objects along the line of sight.
That's definitely true. That's going to have to go into making our cosmological pipelines more complex.
Thanks. So are there any other questions? Okay, so let's thank Lucy again. And I think we can move to the next speaker. That is Srinivasan Raghunathan. I'm really sorry for my bad pronunciation, sorry, from the University of Illinois. And so if you can share your screen, you have 12 minutes plus free for questions to tell us about the first detection of the CMB cluster lensing using polarization data from SPT.
Yeah, although I'm having some issues sharing my screen. I think it works now. Sorry, I think I need to quit Zoom and come back. Oh.
So, in the meantime, if you have any other question or comments from Lindsey, we can take them. Okay.
All right. I think, sorry about that. Can you see my screen now?
Yeah, we see your screen and
All
the
right.
presentation.
Great.
Okay.
Does it look okay?
Yeah.
Okay, great. All right. Yeah, so my name is Srinivasan Raghunathan, and I'm going to talk about CMB cluster lensing. Not really SZ-based measurement, but lensing of the cosmic microwave background. All right. Sorry. All right. So since this is the only CMB lensing talk, I thought I will also introduce a little bit about CMB lensing before showing the results from the first polarization detection. So cosmic microwave background, so that's the remnant radiation from the Big Bang. It's extremely homogeneous, anisotropic radiation. It has a black body spectrum, and it peaks at roughly 2.7 Kelvin. And it's also polarized, and that polarization is because of Thomson scattering at the time of recombination. The other important thing here is that CMB is behind all of the structures that we know, so it's going to be lensed by all of the intervening large-scale structures. And as a result, it has a lot of information about initial moments of the universe, contents and how the universe evolved, and also about structure formation in the universe. And this talk is mostly going to focus on the structure growth in the universe. So Lindsay already mentioned about this, and I don't have to introduce the thermal SZ effect here, but just one slide. So in the context of galaxy cluster surveys, CMB is useful because we detect galaxy clusters using the inverse Compton scattering of CMB photons by free electrons in hot intercluster medium. And this effect is called the thermal Sunyaev-Zel'dovich effect, and it has been used to detect hundreds and thousands of clusters already in the current CMB surveys. Again, I don't have to motivate people about cluster cosmology in this conference, but just one slide. So what I'm showing on this particular slide is how to use clusters as cosmological probes, in particular to probe dark energy equation of state. And this plot shows the expected redshift distribution of SPD 3G-like cluster sample for different values of dark energy equation of state parameter. And you can see that there are clear differences when we tweak the parameter. Of course, I've kept all the other parameters fixed. So yeah, so it's not going to be as awesome as this, but it's going to be a really sensitive probe of dark energy clusters, cluster counts, abundance as a function of mass and redshift. But to do some cosmology like this, obviously we need to infer masses of clusters, and that is difficult. And we have several mass proxies, like the flux from the Sunyaev-Zel'dovich effect, or flux from X-ray, or cluster richness from optical surveys. But pretty much all these proxies have some assumptions, and as a result can be dominated by systematics. And so the clean way of detecting cluster masses or measuring cluster masses is to use weak gravitational lensing. It is less prone to systematics, and at the same time, it can also be used to obtain scaling relations between other mass proxies. So source of gravitational lensing can be cosmic microwave background or galaxies. We have already had a few talks about galaxy weak lensing. So there are both advantages and disadvantages of using CMB. The advantage is that CMB is extremely easy to model in a statistical sense. Its distance is precisely known. It's at a redshift of 1100. And since it's at redshift of 1100 and it's behind all of the clusters that we know, it's easy to find high redshift lenses. The disadvantage is that the signal is very faint, and as a result, we need to stack several clusters. And the current limitations are the number of clusters that we have for stacking, and then the quality of the CMB maps. In the bottom, I'm showing a figure, but I'm showing how powerful CMB lensing is going to be for future surveys. So the plot shows the signal to noise for a single cluster. As I mentioned, it's very weak. It's roughly 1 for a cluster with mass to the 14 solar mass. But what you can see here is that the vertical axis here is mass, and the horizontal axis is redshift, and the color indicates the signal to noise. And you can see that the signal to noise remains roughly constant as a function of redshift. And this is because CMB is behind all the clusters. So this is going to be extremely useful in measuring masses of very high redshift clusters that will be detected by future CMB surveys. So what exactly is this effect? So this is the CMB cluster lensing. On the left, there are these very basic equations, and TQU, or CMB temperature anisotropy, or CMB polarization, which are Stokes Q and U parameters. And you can see that when you have a lens, there is a deflection angle, and so the path of the CMB photon gets bent, and that's exactly what's written on the left. And on the right, I'm showing several figures that illustrates this effect. So on the top panel, so that's the unlensed CMB, zoomed in close to a cluster location. So these are roughly a few arc minutes cross few arc minutes maps. This is a simulation, noiseless simulation. And you have temperature in the first, and then you have a polarization following. The middle panel, it's the lens CMB. And as you can see, that the top panel and the middle panel look pretty much the same. And in this particular case, if you slightly squint, you will see a bump at the center. And this is because of the lensing. And in this particular case, I've used a really massive cluster for this lensing. Otherwise, the signal is very faint. But once you subtract these two things, you see a nice dipole signature. And the other thing that you can see is also that the dipole signature is aligned along the direction of the background CMB gradient. For example, if you look at the bottom left panel, you see that the dipole is aligned along 45 degrees, and that is in alignment with the background gradient from temperature. Right. So this is basically the signal that we want to extract, and we want to use this signal to measure masses of clusters. Okay, so the data sets that went into this measurement, so these are coming from South Pole Telescope. So that's the CMB data. So South Pole Telescope is a 10-meter telescope at the South Pole operating at those 3 bands. We've had 3 generations, and currently we are in the 3rd generation, SPD3G, which is sensitive to both temperature and polarization. The results that I'm going to show, however, are going to use data from SPD Pole survey, which is a 2nd generation survey covering roughly 500 square degrees in the Southern Hemisphere. The cluster sample comes from dark energy survey. So that's the dark energy survey year 3 red mapper cluster catalog. And the bottom, you see a plot which shows the overlap between different SPD fields and dark energy survey. So SPD Pole, which is the tiny square in the figure, so that has full overlap with dark energy survey. So what we do is we take the CMB data and we apply a lensing quadratic estimator, and we extract the lensing signal. So this figure on the left, this is a stacked convergence map at the location of dark energy survey clusters, and this is using CMB temperature. Before going to polarization, I will just tell you about a little bit about temperature. So on the left is a stacked convergence map from 2 different samples, so full sample and a volume limited sample, and on the right we have the radial profile of that convergence map. And you also have, I'm also showing the mass measurements that we obtained using these convergence maps. So we obtained mass, and with that we try to constrain the mass richness scaling relation of dense clusters. The equation is shown here on the left, and on the right I'm showing a plot where we compare the current results with other results in the literature, both CMB and optical lensing. And you can see the results are very consistent with all the other results. However, the error bar is pretty large because CMB lensing is pretty weak currently, but it's improving in the future. I should also mention that when we are trying to constrain the mass richness scaling relation, we are only constraining the normalization because the signal to noise is poor to constrain the slope of this relation currently. So this is temperature. Okay, and let me show this figure comparing. Sorry, my title is all hidden, but the title says expected mass errors from CMB temperature and polarization. This plot on the vertical axis, so that's the mass uncertainty for a stacked cluster sample containing 100,000 clusters. And on the bottom, on the horizontal axis, shows the quality of the CMB maps. So you go towards the left, you're becoming more and more sensitive. So you go to the right side, the map is pretty nicey. Okay. So what you can see is there are different curves. Black color curve is for temperature, and the orange color curve is for polarization. And clearly, we want this curve to be as low as possible because we want the mass errors to be as low as possible. And as you can see, temperature is way better than polarization, and that's because CMB temperature is much brighter than CMB polarization. And the lensing signal is directly proportional to the background magnitude of the background gradient. Okay, so temperature is way more sensitive. So why bother about polarization? And the reason is astrophysical foregrounds. And so let me show this plot. So that's it's same as the left panel, but after including foregrounds. So as you can see here, the orange curve remains the same for different levels of foregrounds. So the solid curve is no foreground, and the dotted curve is having 100% foregrounds. So the orange curve just sits on top of each other. But you can see temperature becomes way worse. So if we had astrophysical foregrounds, temperature becomes much worse. And as a result, we cannot extract a lot of information from temperature because it's now the variance is increased significantly. And this is where polarization comes into key because astrophysical foregrounds are not largely polarized, and as a result, they're not affected significantly by foregrounds. So what we decided to do is to look for this particular signal using, again, SPD pole maps. So we designed a new estimator. Instead of using a lensing quadratic estimator, we designed a really simple estimator that tries to extract this particular dipole signal. The dipole signal that is aligned along the direction of the background CMB gradient, as shown in this particular figure. And here is a plot showing that. This is a plot using a low noise simulation. So one thing that we have to note here is that we cannot simply just stack CMB at different locations, because CMB has random orientations at different locations. So if you stack everything, the signal just vanishes. So what we do is we determine the local gradient magnitude and the orientations to stack multiple clusters. And this plot shows the dipole signature from Stokes-Q and Stokes-U maps for a very low noise simulation. So this is simulation, and the next is data. So this plot shows the results from SPD pole CMB maps, polarization maps, and dark energy survey cluster sample. On the left, so that's a null test. So this is stacking at random locations, and as you can see, you don't see any dipole signal. But on the right, you see a clear signature of the lensing dipole from both Stokes-Q and Stokes-U maps. This is the first detection of the signal, and this was a 4.8 sigma detection, and it was published in 2019 and in PRL. So we use that signal to again calibrate the mass richness relation of the DES cluster sample. And this plot, so Lindsey showed this plot before, and I'm showing this plot again. Equation is given on the left. The right panel shows the likelihood. On the top is the simulation, and on the bottom it's what we get from the data. The solid curve is what we get from polarization measurement, and you can also see yellow color band, which is the measurement that we get from temperature, and the red color hatched bars, which comes from dark energy survey. So as you can see, it's consistent. Our results are consistent with previous results, but the error bar is pretty large. But it's improving, like Lindsey mentioned. So this is SPD pole. With SPD 3G, the sensitivity has increased roughly an order of magnitude the number of detectors. So sensitivity has improved significantly. So let me just finish by showing what we expect from the future. Just the last couple of slides. Lindsey mentioned this already. So this is what we expect from future CMB Sanya-Zeldovich surveys. And this is in particular for the CMB stage 4 experiment. So it's the next generation ground-based CMB experiment that will give us roughly 2,000 clusters above redshift of 2. This is amazing. And we have all of these clusters. We'll get all of these clusters, but there is no way to measure their masses because you need dedicated follow-up lensing observations, which are very expensive. So CMB is the only way to calibrate their masses. And in particular, for this very high redshift clusters. The plots here on the left, it's showing the limiting mass as a function of redshift. So vertical axis is the mass of the cluster. Horizontal axis is the redshift. And as you can see, we are going below 10 to the 14 solar mass, even at very high redshifts. And on the right, it's the cumulative redshift distribution of clusters expected from CMB stage 4. And as Lindsey mentioned, the green color solid line, so that's for CMB stage 4, and we expect roughly 70,000 to 100,000 clusters from this. And in particular, the box that is highlighted, so that's the unique discovery space for future SE surveys, because all of the low redshift clusters will be captured by LSST. So that's my final slide. So what can you do with these clusters? In particular, I want to highlight the fact that CMB lensing is extremely important for this. So this plot shows the constraints on cosmology and also astrophysics with and without CMB lensing. So the pink color curve, so that's the constraints that we get if we do not include any lensing information. And the green color curve, so that's the constraint that we get after including CMB lensing. And the parameters that we are trying to constrain here are astrophysics, so 1 minus b. And as you can see, we get sub% level constraint on that. Neutrino masses, dark energy equation of state, we get roughly a factor of 2 to 3 improvement when we include CMB lensing. The other important thing here is that I said we detect high redshift clusters, but we have no idea how those high redshift clusters are going to be. So we also try to model their visualization process. And this is the first time that we think we can constrain the visualization mechanism of high redshift clusters using CMB. With that, I will go to my summary slide. So summary is that galaxy clusters lens the CMB, which can be used as a mass proxy. And I showed results from both temperature and the first detection of the polarized lensing signal using South Pole telescope. I also wanted to highlight that astrophysical foregrounds are less important for CMB polarization, and so CMB polarization is going to be a key measurement for the future. And future SZ surveys return roughly 1,000 clusters about Redshift 2. CMB lensing signal to noise looks promising, and we get roughly 2 to 3 improvement in astrophysical and cosmological constraint using CMB lensing-based mass calibration. The other important thing here is also to highlight the fact that CMB lensing is highly complementary to galaxy weak lensing measurements, because many of the systematics are uncorrelated. But there are certain systematics that are correlated, like baryonic effects, centroid shifts, projection effects that need more attention. And I'll stop with that. And yeah, thanks for listening, and thanks to the organizers for giving the opportunity.
Thank you for your nice talk. So we see if there is, yeah, from Marina and Andrea. Okay, so let's start with Marina, please.
Yes. Hi, thank you for your presentation. And I just wanted to know, so maybe I did not understand. So is it possible, so right now you measured the CMB lensing either from temperature or polarization. Mm-hmm. So is it possible just to combine the two to make the analysis, or
correct? Yeah. So in fact,
in
this particular plot, I've combined measurements from both CMB lensing, but from both temperature and polarization. Yeah. So yes, so we can definitely combine those measurements.
So it's not polarization alone. It's polarization plus.
This particular plot has both temperature and polarization. Yes.
Okay. Thank you.
Yeah. Right. Nice.
Andrea.
Very, very impressive. Can you develop a bit about the last thing you said? How you're going to constrain the realization mechanism?
Right. Yeah. So in this particular paper, we tried a really simple model, and the model is actually given here. For example, you have to like rotate your head. So there is, I call it model 1, and there is an equation where we call it V of Z. So that's the realization efficiency as a function of redshift, and we assume this very simple linear scaling where we have a parameter called eta. That's the realization efficiency of clusters. And then we have this 1 minus b parameter with a slope. So that's one model. That's a very simple linear scaling. And then on the upper diagonal, we have this other model where we try to constrain the same thing but using simulations. So this particular model has been developed by Daisuke Nagai and a student Han Ong. I think I do have a slide showing.
I don't think we have time to if you can continue during in the discussion, like, and also other question. I think I cannot take them because otherwise we don't have time for the other speakers. I'm sorry. I mean, you can write in the chat. Just remember to put the name of the speaker at the beginning. Sorry.
No worries. Yeah. Thank you. Thanks all.
Thank you again. So we can move to Sebastian, if you stop to share your screen, okay? So Sebastian Bocquet will be our next speaker from LMU, and we'll talk about the weak lensing, the weak lensing calibrated cluster cosmology with SPT. So please go, you have 12 minutes.
Yep. Are you seeing the slides the way?
Yeah,
it should be?
Yeah.
Cool. Okay. So first, I'd like to thank the organizers for the invitation. I was asked to talk about anything related to the SZ effect and cluster masses. And so here I'm giving kind of a status report on where we're at with SPT cluster cosmology. So luckily, all the introductions have been presented, so I can get right into things. And so I'll start with where we're at today and where we're heading in the next couple months, basically. So to do cluster cosmology, as you know, you need to do a couple steps. First one is you'll actually find clusters. And as Lindsey discussed, we're using the South Pole Telescope and find clusters in the millimeter wave sky. The next step, once you have your SZ cluster sample, is you get multi-wavelength follow-up data, including redshifts. And so here I'm showing the sample as of 2019, and I'll talk about more recent things in a minute. So if you just look at the plot on the left-hand side here, That's the cosmology subsample of the SPT cluster sample. And the important point here is if you look at the black crosses, these are the SPT samples with redshifts and estimated masses. And if you now look at the colored highlighted points, these show multi-wavelength follow-up data. So the blue points are clusters for which we have X-ray follow-up data. Green is weak lensing data from ground-based telescopes, MegaCam on Magellan in this case. And orange is our high redshift space-based weak lensing follow-up using Hubble, as discussed by Tim Schrabback a couple minutes ago. So now we're using all these data to do our mass calibration and cosmology analysis. And before getting into the details, I'd just like to highlight a probably obvious point, which I call the mass calibration premise. So basically, we could, in principle, use the SZ mass relation that we get from first principles or from numerical simulations. The reason why we do not do that is that such an approach would be systematically limited by the unknown strength of baryonic feedback effects. So just like to emphasize this point, that's why we're all doing these weak lensing mass calibration analyses. And that's because the weak lensing to halo mass relationship is much less affected by gastrophysics. And so we're much more confident that we're able to map halo mass to the lensing signal, as obviously many have discussed in this meeting already. So as a result, we're using weak lensing data to constrain the mean scaling relations. So now back to the actual analysis. I have 2 slides on the mass calibration. So first, the weak lensing part. As described by Tim and Lindsey, we're using this MegaCam and Hubble data set. And so starting from our SZ mass scaling relation for SPT clusters with a priori unknown parameters, and these parameters are normalization, mass slope, redshift evolution, and scatter. If we then add the weak lensing data set together with a known relationship between the lensing signal and halo mass, we're able to calibrate the mean SZ mass scaling relation. And that's shown in this figure here from Jörg Dietrich's paper. We're plotting the weak lensing inferred mass versus the SPT SZ signal. And as you see, we're able to obtain a best fit relationship. Okay, part B in mass calibration is to look at scatter a little bit more. In our analysis, we actually added a third mass proxy, so a second low scatter mass proxy, which is the X-ray YX quantity, again with a priori unknown scaling relation parameters. And what happens is shown in this plot here. As you would expect, the Z scatter and the X-ray scatter are degenerate. And importantly, the data alone are able to place an upper limit on scatter. And if you actually look at the full marginalized 1D posteriors, we're able to constrain the Z scatter. So as a result, if we use weak lensing mass calibration and this second low scatter mass proxy, we have calibrated the full SZ mass scaling relation. Now, just for prospects, you can look, for example, at a paper by Sebastian Grandis for how we should be able to constrain the scatter from weak lensing data alone in future surveys, and many others who are present here have had these thoughts as well. Okay, so now let's look at the actual cosmological analysis. So what we did is a simultaneous mass calibration and cluster abundance analysis. Again, the sample as of 2019 were 343 SZ selected clusters, of which 32 have weak lensing data and 89 have X-ray follow-up data. Again, we start with wide flat priors on the SZ scaling relation parameters, and they fully encompass the posterior, which is calibrated from the weak lensing data. So on the right-hand side, you see our key plot for lambda CDM with massive neutrinos. You see omega matter and sigma 8. The blue contours are the SPT results. And you see here how they compare with other state-of-the-art results as of 2019. So this was also discussed by Lindsey a couple minutes ago. At the bottom left, we now see if our model is able to explain the data. So we see the abundance as a function of redshift and the SPT detection significance. The histogram are the data, and then the green lines are the mean recovered model, and everything looks good. Another test we did is to more directly look at growth of structure by trying to measure sigma 8 as a function of redshift. So the way to read this plot is the following. The red band here is the Planck primary CME anisotropies together with the Lambda-CDM model. And then the blue and orange points are the following analysis. We use Planck to constrain the expansion history of the universe, and then the SPT clusters to constrain the growth. So blue points are then our fiducial results, assuming a single SZ scaling relation with the weak lensing mask calibration and everything. And then orange is a model that has even more freedom, so we allow for separate SZ amplitudes in each redshift bin. And then the takeaway from this plot is that, as you would expect, sigma 8 from the clusters is lower than what Planck prefers. That's the well-known shift in sigma 8. But the important point is that this offset seems to be rather constant with redshift, indicating that there's nothing completely crazy happening. And the cool thing is really the redshift range we're able to probe here, and this will only get better with more data. So now I'd like to switch gears and discuss what we're currently working on. So how to improve upon what I've shown so far. So as is the theme of this conference, we're lucky to be in the era of wide field surveys from multi-wavelength data sets. So what we're going to do is use larger cluster samples and more weak lensing data. So some recent progress that we're lucky that these were discussed by Lindsey and Tim a couple minutes ago. So I'm just going to briefly recap that on the left-hand side here, we see that we have a lot more SZ data, deeper SZ data, so we have bigger SPT selected cluster catalogs. And then on the right-hand side, Tim already discussed how we're pushing high redshift weak lensing mask calibration. And I'd just like to highlight this plot again, where really you see that we're able to start to map out the redshift evolution of the SZ signal over a wide range in redshift. And finally, just a shout out to the upcoming paper by Hannah Zorn, where she's adding even more clusters basically to the right of this plot beyond redshift 1.1. The other element that I'm actively working on is still in this plot here from Lindsey, is to use DES weak lensing mask calibration at low and intermediate cluster redshifts. So we're using the dark energy survey data for that. The important point is really that there's a huge overlap between the dark energy survey, which is the green outlines here, and the SPT surveys, which are the colored outlines. And so this is really a fantastic weak lensing data set. And now let's look at what we can do with it. So what we want to combine is the SPT SZ and SPT POL cluster catalogs with DS Year 3 weak lensing mask calibration. This will give us roughly 1,000 SPT selected clusters over more than 5,000 square degrees. And as Lindsey said, this is then the full pre-SPT3G dataset. We're using DS weak lensing data up to cluster redshifts of about 0.85. And this means that we have 700 weak lensing clusters. And we're doing a cluster by cluster weak lensing analysis, no stacking. Currently, we've validated the analysis code using MOX, and that's where this projection on the right-hand side comes from. So the dark blue contours are our latest published analysis from SPT-SZ with the targeted megacam and HST weak lensing data sets. Light blue is Planck primary CMB anisotropies, and then red is our projection for this SPT-SZ plus SPT POL plus DS-U3 analysis. The analysis using the real data will be performed blinded with an unknown shift at the parameter level. As usual, this is to avoid any subconscious bias. Since this was brought up a couple minutes ago, one of the things we want to check while being blind is if our choice of using optical or SZ centers for weak lensing has an effect on the outcome. The idea being that if we know how to correct for miscentering, this shouldn't matter. So that's the kind of analysis we want to do. Now, I'd briefly like to highlight one slide about the DS-U3 cluster, weak lensing data set. So in the top row here, I'm showing the systematic uncertainty in lensing efficiency, or inverse sigma critical. And this systematic uncertainty is sourced by the uncertainty in photo Z calibration and shear calibration. So the way to read this plot is you have the different colored bands that represent the different tomographic bins in DSC3 data. And then you have the purple band in the middle, that's the systematic uncertainty in DSC1 data. And so you see that the DS weak lensing folks have done a terrific job in reducing these systematic uncertainties significantly. Now let's look at the statistical constraining power. That's the bottom row. Here I'm stacking all SPT clusters with a detection significance greater than 4.5 in roughly the one halo term regime. And I get a shear signal to noise here of 80, so plenty of signal to work with. So one last slide about the full weak lensing model, since that was brought up in previous talks today, as we're following this recent paper by Sebastian Grandis, and we combine all weak lensing modeling ingredients into a single simple framework that enables an efficient likelihood analysis and a cosmology analysis. So this model, as was discussed, for example, by Henk, contains the mass modeling, shear modeling, and we actually do relate full physics halo profiles to the gravity-only halo mass function, specifically to address this point that Henk brought up rightfully a couple minutes ago. In addition to doing that, we compare these results from using two different sets of hydro simulations, so the Magneticum hydro simulations and the illustrious TNG simulations. And we do indeed find that depending on the hydro implementation, our weak lensing mass calibration changes by 2% in mass. And so we're folding this uncertainty into our error budget. So at the end of the day, we have a total systematic weak lensing uncertainty of less than 6% as a function of cluster redshift. And with that, it's time to come to my summary slide. So the main takeaway is that these really nice SPT plus DS results are coming up. This is a combination of wide field surveys. Important is that we're not yet saturating the systematic floor in weak lensing. And then two other prospects, as discussed, weak lensing mass calibration beyond redshift of about 0.9 still remains rather uncertain, despite very nice HST lensing programs going on. And we've heard about CMB lensing that should really help to nail down mass calibration at higher redshifts. And with that, I'm ready for your questions. Thank you.
Thank you. Is there any question? No. But we can continue to, oh, okay, Gary. Go, Gary.
Okay, thanks for this nice talk, Sebastian. This is fantastic work. I just wanted to ask a side question. So do the SZ measurements today, or do they have enough resolution that we can have a handle on the offset between the optical position of the brightest cluster galaxy and the SZ center?
Yes. Sorry, I'm hesitating because that's stuff that we're discussing basically right now. But yeah, basically we are looking at the off-centering distributions, and this has been looked into before, for example, in papers by Alex Saro or Lindsey Bleem. Obviously, the SPT positions obviously do take a hit by the rather large SPT beam. But yeah, that's definitely part of the mix in determining the miscentering distributions, as was brought up by other speakers today. And I think really where we're heading is obviously, again, to do the multi-wavelength approach, where, you know, if we combine observations of optical centers, SZ centers, and X-ray centers, we really should be able to learn a lot about how to, how to pick the kind of centers we want, and how to, most importantly, estimate the uncertainties.
So you think you'll have answers in a few months or a year?
Well, the plan is a few months. What the answer exactly will be, I think we still need to see.
Okay, thank you very much, Sebastian.
Thank you.
Okay, so thank you. I will take the advantages, if we don't have any other question, to go to the next speaker so we can gain a few minutes. And So if Nick, you could share your screen. Okay. So the last talk of before the break will be by Nick Battaglia from the Cornell University, that we talk about AZ cluster masses from the ACT perspective. So you have 12 minutes, so we have 30 minutes for the question. Please start.
Great, thanks. Can you hear me okay?
Yes.
Okay, great. First, I'd like to thank the organizers, especially Lindsey and Bruno, for their patience with me and the delays and so on and so forth. But again, thank you for the invitation to speak. So in these next 12 minutes, I'm going to try and summarize all the ACT results that the SBT collaboration had the past hour and a half to summarize. So I'll do my best. It's going to be very shallow, but please feel free to ask questions and we can go much deeper. So Naomi already gave a really nice introduction to ACT. I just wanted to emphasize what you get from going to the ground. On the right here, you have Planck. On the left, you have ACT, and you can make a similar movie with SBT, and you can really see the difference in terms of noise and resolution you have by being on the ground, being able to stare much longer, and you can really see things like SC clusters really just start to pop out by eye. So I'm just putting my cursor over various clusters that eventually pop up there. And not only do we have this over, we have this depth and this resolution over large areas of sky. So this is a map of the current ACT status made by Sigurd Ness. Well, not that current, but as of 2018. This is showing 18,000 square degrees, where for the most part, we are 4 to 5 times deeper than the Planck satellite. And we are currently still taking data in our season 2021 here, where we have three different cameras on the sky. Both of them are dichroic, and we're observing in 4 frequencies here. Okay, so this data set is great, and it's only going to get better. And as you see, when we have this great multi-frequency CMB data with this high resolution, we can find lots of clusters. So this is our latest cluster catalog. This is from Hilton et al. 2020. And as you can see here, we're covering now, we've cut out some of the sky that has the galaxy in it, but we're still roughly surveying, at least for galaxy clusters, 13,000 square degrees. And we're using 2 frequencies, 90 and 150, to find clusters here. There are over 4,000 clusters that we have confirmed. A lot of them are new, almost 900 of them are new, and a lot of them are at high redshift. So redshift so there's 200 plus at redshift 1 or greater. You'll notice that these crosses here, these blue crosses, show you where we're finding clusters. You notice they tend to cluster, and that has to do with just the varying depths we have on the sky with ACT. Because we didn't necessarily decide to go wide right away. We decided to go deep in certain regions, and so we have better data in some of the regions here, like what we call our deep 5-6 region, which overlaps with Stripe 82, or in our Boss North region, which overlaps with the Boss North field over here. And again, this is all published. This is out there. This is just a nice movie of what that catalog looks like on the sky in 3D, but I will skip ahead and just show you the mass and redshift distribution. So updating Sebastian's plot, showing you ACT and SBT clusters here. You can see this nice sort of cut in mass and redshift, our very straight line that Lindsey alluded to earlier, making SC, I think, a really great proxy for your selection function. But there's lots of clusters here, right? There's, at least in the blue, 4,000 points. And there's still more clusters to be confirmed out here, as we just need to follow up some of our high signal to noise objects here. So this is still incomplete in terms of our follow-up. But getting to the topic of this conference, right? Cluster masses. So where does this mass come in, right? We've done a mass calibration. But just to reiterate what Lindsey was saying, right, we have the integrated Compton-wise signal. This roughly scales like mass to the 5/3. But as Sebastian and others have alluded to, right? The difference is there's astrophysics, right? So the AGN feedback, star formation, et cetera, affects the distribution of the free electrons that do this Compton upscattering of CMB photons. It also affects their temperature, right? So we can't predict this a priori from theory or simulations simply because we don't really understand the physics that well of these complicated processes. So what ACT does is, as Lindsey pointed out, we use a filter. We use, in this particular case, a 2-band filter, but we used a fixed aperture. We're not changing our aperture. The aperture is 2.4 arc minutes, and we get what we call our Y twiddle. And this Y twiddle roughly corresponds to mass, given some initial guess at what the electron pressure distribution looks like in galaxies or galaxy clusters, but we actually really need to calibrate that to get the mass. So what I'm going to do over the next couple slides is show you some of the ways we are calibrating masses within ACT. Again, at a very surface level, giving you some examples. So we already heard from Naomi about what we're doing with kids. Here's another example from the HyperSuPrime survey. So this is on the Subaru telescope. Eventually, this HSC survey will get to 1400 square degrees. But right now, and it'll completely overlap with our advanced ACT. As you can see, we cover lots of area. But this is from their initial release, from their 2018 release, where we only had 8 clusters that overlapped with the HSC region. But even though there are only 8 clusters, this is showing you the weak lensing signal. You can see it's actually really, really nice. This is a 8 cluster stack. The total stack, significance of this total stack is 11. And with this, we are actually able to start measuring cluster masses, shown up here on the right. One thing I want to point out here is we fit this data with various different models. One of them was just, as Keiichi pointed out yesterday, which is known as the single mass bin fit. So fitting just a single mass bin for your stack. As you can see, if we do a different sort of forward model or a stacked model, as Keiichi was pointing out, we actually have different masses here. So we're already in this regime at, signal to noise is above 10, where these differences are starting to matter. Another thing we did was we used N-body simulations and full hydro simulations to fit. And you can see, again, on the same data, we're inferring different masses that are different on the order of about 10%. So this is a systematic, right, that we've already heard about from Henk and other people of Henk. We heard from Sebastian. We heard from Tim about various ways people are trying to account for this systematic from baryons when we try to infer cluster masses. So I wanted to take the opportunity to mention some work that a student who's working with me, Dylan Cromer, has done. And we have a different model for accounting for baryons and optical weak lensing. So this has nothing to do with ACT, but we're fully forward modeling the weak lensing signal, assuming a pretty simple baryon plus dark matter profile for the cluster. Here, the baryon profile is not fixed. It has free parameters. It's a GNFW profile where we allow the outer slope and intermediate slope to vary. We marginalize over the 2 halo term. And what Dylan's done, which is really nice, is he's come up with a really quick way to integrate this into the delta sigma, our weak lensing estimator that we use. And so he created an emulator and he models the stack, right? We don't want to do this single mass bin fit. We know that's biased. And what I'm showing you here on the right is results for sort of mock Rubin-like observations of a large sample of simulated clusters. And you can see when we do our baryon fit plus our 2 halo, we get an unbiased measurement of the weak lensing, the true weak lensing mass, because we know it from simulations, albeit with a little larger error bars, right? Our precision goes down a little bit because we're marginalizing over the intermediate slope and outer slope of the baryon profile. But that being said, we could actually constrain these 2 parameters with other measurements. We are measuring gas profiles of clusters via X-ray observations. We can get it with SZ if we have joint KSZ and TSZ observations. So in principle, we can actually empirically constrain these rather than having them be completely free. But as you can see, if we just did NFW only, we are biased. So that is the key. Okay, so this
you
is
have 3 minutes.
Yeah, I saw. Thank you, Barbara. Another thing we're doing, as we heard from Srini, is we are doing CMB halo lensing. So this is temperature only. I'm showing you a measurement not of SZ clusters, but this is of mad cow clusters. So these are high redshift or highest redshift optically selected clusters. We did this after all the cuts on almost 700 clusters. This is showing you the result. Here's the profile here. This is the filtered mass profile as a function of distance from the center. Here's what it actually looks like in the signal in the stack. And this is about a 4 sigma measurement where we're constraining the mass roughly to be about 1.7 times 10 to the 14 solar masses on average for the mad cows clusters. I'll point out that we do have SC clusters. We are just in the final stages of putting this out. And I'll let you do the math. We're doing this on all our SC clusters, so about 4,000 clusters. And our SC clusters are a little bit more massive than the mad cow clusters. So you can guess at what the signal to noise of this is going to be. Or I can do the calculation for you. We also looked at things like comparing richness and Compton Y, as people have seen with mad cows. And we're also doing this within DES as well, and HSC and with the Chimera clusters. And one thing we noticed, I just wanted to point this out, is that there's a significant fraction of SC signals missing for these mad cow clusters. So we only got almost 60% or 3/5 of the clusters had a detectable SC signal, right? So this, supposes that maybe a lot of these mad cow clusters have dropped below our detection significance for ACT, or maybe there's some line of sight alignments. We also noticed that a lot of optically confirmed ACT clusters within the same volume as the mad cow sample were not selected in mad cows. So there's some really interesting things going on here with the different selection functions between, say, an SC selected sample and an optically selected sample. In particular, this is specifically for mad cows, but other people have looked into this for other optically selected clusters. Or I should say, this should be IR selected, I guess. So looking ahead, right, these are just 3 examples. Again, I had 12 minutes to show you some of the things we were doing, but this is an ongoing effort within ACT with many people within the collaboration as well as other collaborations. So just to name a few, we do have an updated measurement from HSC on our weak lensing mass calibrations that we're working on at the moment. There's also DES mass calibrations of ACT clusters. As you can see, the SC footprint the DES footprint completely overlaps with the ACT survey. And we have the CMB halo lensing mass calibration coming up that I mentioned, which is definitely a higher signal to noise than that 4 sigma measurement that I showed you. We saw Naomi's talk, right, on the KITS mass calibration, and there is some work on doing joint CMB halo lensing calibration and optical weak lensing mass calibration. And as I mentioned, I'm going to continue to work within my group here on the theoretical and systematic modeling of the mass inferences. So, and before I end, as we know, Advanced ACT is ending soon, and Simon's Observatory and CCAT Prime are going to be on the sky shortly after, where we're going to get deeper data roughly in the same footprint as what Advanced ACT had at the same resolution. So, this is very, very exciting going forward. And just to plug, as Lindsey pointed out, I do have a lot of interesting things to say about profiles. But again, we were talking about masses here, but if you do have any questions about profiles, I do have extra slides. So thank you very much. And if you have any questions, please.
Thank you. So are there any questions? So yeah, Sebastian?
Hi, Nick. Thank you very much for the nice talk. I was wondering, here you mentioned the joint CMB halo lensing and weak lensing calibration. And as Srini pointed out, some of the aspects should be correlated between the two, like halo profiles and so on. Do you have like a quantitative numbers on how big this correlation is?
Well, so for the actual inference, the correlation should be 100%, right?
Yeah, but okay, then I guess in the total mass calibration budget, how much, like how bad is this correlation? Do you guys already have those numbers?
We do not have those numbers. Here we're really interested in sort of the different systematics in the actual measurement. So, Henk said earlier on, right, that the systematics are getting really well understood for weak lensing, optical weak lensing calibration. CMB lensing, CMB halo lensing is going to have completely different systematics. And we're in a regime now, as Srini pointed out, where the CMB halo lensing, especially at the higher redshifts, is really starting to catch up to the optical weak lensing, right? So we can really start to do this comparison where we have different observational systematics, right? Measurement systematics. But yeah, we haven't really looked at we haven't gotten an answer yet to what the sort of mass inference systematics will be when we do this joint analysis, which is a really interesting question, especially if we want to start, combining these going forward for cosmological analyses.
Okay, thank you.
Okay, so I think we have to go for the break. I was saying Gus. So maybe we can discuss. I mean, in the final discussion, we can go on with also talking about the profiles. I'm very interesting to. For me, it would be very interesting to hear about that. So we will have the break, and we have to reconvene here at 5:55 for the Central Europe time.
Yes, 5:55.
Okay. Thank you to all the speakers again.
Let's have a short coffee break. Thank you, Barbara.
Thanks.
Gus, I'm still here if you want to ask your question.
Well, I would be curious to see your slides in the profile, if it's possible.
Me too.
Right. So the reason why I didn't show this, right, because these are measurements of sort of group scales, right? So we're cross-correlating sort of C-mass galaxies, right? These are 10 to the 13 solar masses. But through this cross-correlation, we were able to pull out the density profile via the kinetic SE effect and the gas pressure, right, just through stacking, traditional stacking of these clusters on something like a Compton Y map, or in principle, just on the raw maps, right? And you can extract the signal there. And so this is what the density profiles look like from our KSE measurement, right? And what's kind of nice is, we detect the KSE, at least from a null detection standpoint, right? We rule out a null detection of the KSE at, 6 to 8 sigma, depending on how you count. We've also shown that the gas profiles in these objects look nothing like an NFW profile at like 90 sigma. And this, can vary depending on exactly how you choose your NFW profile. So the gas is a lot more extended, but that's not too surprising for anybody that's not a cosmologist, right?
Okay. So you choose, you have to use a low mass object, or you choose to do it, or
for here, you don't have to choose low mass objects, but you need to do the cross correlation if you want to get rid of, if you were to just stack and look for the KSE because velocity is parity odd, right? They can either be moving away from us or towards us. It'll null out the signal unless the universe is moving in one direction, which it's not, right? So so you need to do a velocity reconstruction, so that you need a spectroscopic sample of galaxies, and that needs to be at high density. So it needs to be at the ability to do velocity reconstruction for, say, BAO, right? Baryonic acoustic oscillation. So here, CMAS already existed. In principle, you can do this for clusters, but you take a hit from the CMB noise. So it really helps to have more objects to beat down, right? Because KSE looks exactly like the CMB to first order.
Yeah. So in principle, you can take a concentrated cluster, but then you are concentrated biased. So
yeah. So in principle, you can pick clusters that are within the large scale velocity reconstruction that you've made from the galaxies, but there will be a velocity bias, as you pointed out. But that's how we get the density profile. You can do this, it's trivial to get, well, it's been done many times to get the TSE profile, right? In these objects, this is a much higher signal to noise measurement. You have to be aware of dust, though, because these are lower mass, they're not galaxy clusters. So we needed to remove the dust. We used some higher frequencies to do that. And then this is, something that the simulators can maybe talk about. We compared to then simulations, right? We take simulations, the TNG simulations, my old simulations, we put them in, forward modeled them through to the observations. And, you can see here the density profiles. This isn't actually too significant. These are highly correlated errors out here. But, in the pressure, it just looks like the simulations don't produce enough hot gas in these sort of group scale objects. And this is translated down in here into sort of the 3D profiles that we're all, theorists are used to looking at. So
that's for sure. This we can discuss in the final discussion on simulations. So yeah, okay, yeah, very interesting.
Sorry, I think Norma has a question.
Yeah, but I mean, I'm not anymore in the chair position, so since it's the break, anyone is free to speak.
I don't know. Good afternoon from Paris. I don't know if I am allowed to ask a question now if there is time. Anyway.
Yeah, of course, we are in the break, so.
Oh, thank you. Yes, about the profiles. I am wondering. It's very nice all your observations and the plot you show. And I am wondering about why you show only one profile as the predicted from simulation set, having the very clear fact and from many years that you have a big difference from the best fit profile from the observations, which become more and more precise, and all what we know, and this particular profile from the simulation, from the simulation or whatever, the predicted profile you show with the points. And so what other profiles? Now, how could you improve these nice plots showing other profiles which predict much more agreement with the observations? Because I think that now, it's time to integrate in some way or to take data from the different progresses from the clusters, in particular cluster surveys, observations, all what we are looking, what we are hearing here. So this question is perhaps for you, but not only for you, but you are the first perhaps that are showing the profiles, which I think is a key point in this subject.
Yeah, no, Norma, thank you. That's a great point. So this analysis was limited to our person power, our ability to take the simulations, run them through forward model to the observations, because these aren't just standard profiles, right? We need to convolve with the ACT beam. We need to do aperture photometry and all that. That being said, so after the fact, we did do this calculation for the Planck pressure profile, right? So this is the pressure profile that Planck calibrated on Planck clusters, right, through a stacking analysis. And it looks very similar, not surprisingly, because they showed a comparison to my old simulations. It looks very, very similar to this pink profile. I know other people that have taken this data and done comparisons to the Eagles simulation, which is really nice. And then again, you get similar results to the TNG profile shown here. Maybe it's in between what I did in the past and what TNG is shown now. But yes, I agree. We can, it just takes time, right? These analyses, getting a hold of the simulations, making the profiles, then fully forward modeling it through our pipeline. It's just a matter of time and getting a hold of the simulations. But this data is public, so people are welcome to take it. The forward modeling pipeline is public. So again, people can take that if they use it correctly, they should be able to reproduce our results as well as then put in their own simulations. But I agree, there's many other profiles out there. We are just limited in terms of our person power, person hours to compare with more profiles.
So your plots on the upper left and the upper right between the kinetic cumulative and the, I think it's cumulative, right? And the thermal differentials seem to be inconsistent between your comparison to TNG. And the reason why I say this is that the points on the left on the outer parts are increasing faster and faster with the models, whereas they're going decreasing faster and faster in the other direction. So I don't know, maybe I'm wrong. So did you?
That's a correct observation, Gary. I just wanted to point out, right? This is the decrement. So higher signal here means more pressure. Oh, yeah, whereas, yeah. So this is more density. This is more pressure. So that's
negative. Yeah, I didn't see that. So how do you get the density of the gas? What do you assume for the temperature? Do you take it from some X-ray analysis?
We don't assume anything for the temperature, right? The kinetic SC is proportional to the peculiar velocity and the density, right? Okay, and so through our cross-correlation analysis, the peculiar velocity actually drops out, and just in the way our estimator is constructed, and that's purely determined, it becomes an overall amplitude, and that's purely determined by cosmology, right? And is, you know, pretty insensitive to cosmology. So what's left over, or at least the shape, right, it shows us the shape of the density profile, the cumulative density profile.
Okay, and so can you compare your density profile to what people have been talking about 30 years ago, like these beta profiles that the X-ray people have been talking about?
Sure. Yeah. Again, these are different scales, but we can put on beta profile. Yeah. I mean, if you have a 3D density, gas density profile, we can put it into our model and completely forward model it through and put it in here. Again, we are just limited in terms of the amount of hours we had to put into this. But yeah, we could totally do that. Again, there's, you know, an order of magnitude different mass scales, but you know, we could always do that. We could do that test.
And what the pink curves are an older work of yours?
These are all. This is like 2010.
Is it based on other data?
No. So this was you know, simulations I ran back during my thesis, just wanting to study the impacts of AGN feedback on the SC. It turns out it was important. And so, you know, these are simulations that have been used to compare against the Planck data when it came out and things like that. So I just, you know, I had it. It was, you know, the profiles were already made, so it was pretty easy for me to use and for my group to use. But yeah, I mean, this is a whole other talk that I give a full colloquium on. But I should point out, this is work led by Stefania Modio, who's now in Strasbourg, and Manuel Shan and Simone Ferrara also did a lot here. I was just...
It's very impressive because the kinetic signal is very weak, especially for groups. And so that's a tour de force.
Yeah. But luckily it falls off like mass. So we actually, as you go to lower and lower masses, the kinetic SZ actually becomes much stronger than the thermal SZ. So we're sort of getting towards the sweet spot. It sort of transitions around 10 to the 12 solar masses. But you know, getting down there is really, really tough. We don't quite have the data to do that yet, but we're hoping to get there with.
And what was your group sample?
This is the CMAS sample from BOSS.
Okay.
So it's a spectroscopic sample. You need a spectroscopic sample in particular for this type of measurement, or at least a background spectroscopic sample. There's some work going on within ACT where we're trying to do another method that uses a background spectroscopic sample to reconstruct the velocity field.
And do you remember how many groups there were?
In this particular analysis, we are over 200,000 objects.
Okay.
But this is going to grow. We're going to get more objects with DESI, which has a very similar footprint to BOSS. And you know, once we get this this is sort of, again, it's a stacking analysis. So the signal to noise goes like square root n, right? So we're going to get an order of magnitude more galaxies. So that's exciting. The data is going to get, factors of 3 or 4 better, again, which helps with the stacking analysis. So this is, just going to keep, these error bars are going to keep shrinking, and there are going to be new tests, right, for these simulations, which don't calibrate on these properties, right? These are new. They've actually made predictions, which is really nice for hydrodynamic simulations.
Great. Thanks, Nick.
Excuse me. For the profile on pressure, you are meaning only gas pressure profile?
Yes.
Or the total here in your slide, the last picture is on the only gas, the pressure, or is the total one, or is
great question. So the thermal SC is specifically sensitive to the electron pressure, right, which you can translate to the thermal pressure. So it's not the total, right? We don't include non-thermal pressure because we don't measure it. But in principle, you can infer what the non-thermal pressure is because you have the thermal pressure, you have the gas, and you have with lensing, you can get an idea of what the mass is, right? And then you can solve for what the non-thermal contribution is.
Yes, precisely.
I will have to interrupt this discussion because the coffee break is almost over. Well, not for everybody. But yes, I needed you to not enter your screen. Yes, right. Thanks, Nick.
Sorry, Bruno.
No problem.
But yes, Norma, that's correct. You can get the non-thermal pressure if you want.
I think that is very important to infer and to have, and from that the equation of a state, the same for the profile. So there is work to do, but reachable, I mean, realistic work. Thank you.
Sorry, share screen. Am I sharing the screen now? Full screen? I can't see that. So
it's not quite full screen.
It's not full screen. Oh, sorry. Yes, you like that, right?
Yeah.
All right. So let's start this flash talk session. So we'll try to stick to the 1 minute per slide, which is fast, but let's go ahead. And the first one is Caio Lima de Oliveira. I think you're online. If you want to start.
Hi, good afternoon. My name is Caio Oliveira, and I'm a master's student at State University of Londrina in Brazil. I'm working on the comparison of bins and unbinned analysis of weak lensing data for the mass estimate of galaxy clusters. Specifically, I'm using the CLMM library made by the LSST desk team and the non-Cosmo library developed by iDevices and on which I'm starting to work on. On the slide, you can see that the results of one of the examples on CLMM using non-Cosmo as the background engine. The horizontal axis of corner plot shows the log 10 of the mass of the cluster, and the vertical one shows the concentration. We can see that the purple graph, which shows the unbinned analysis, seems very promising when compared to the blue, which shows the binned one. Our plan is to continue developing a stable and efficient method for unbinned analysis.
Thank you. Thank you, Caio.
Thank you.
So the next poster is from Jacqueline McCleary.
Hello. This is an advertisement / preview of something to come in the spring. as we heard from Henk's talk, cluster weak lensing requires accurate galaxy shapes, well-measured ones, and accurate colors. These things can be very challenging to get from the ground, so I present SuperBit, a diffraction-limited imaging platform that flies 30 kilometers above the ground. It's been engineered to have diffraction-limited imaging over a field of view 36 times larger than ACS, and has almost perfect blue transmission. In fact, it's so good, we'll be doing our shape measurements of about 46 galaxy clusters in a blue band. Our flight is scheduled for spring 2022, and we hope to deliver a really unique weak lensing data set of 40-ish massive, well-studied galaxy clusters.
Thank you very much, Jacqueline. Fascinating. Next talk, next poster from Alex Maltz. Are you online?
Yeah, so my name is Alex Maltz. I'm a postdoc at the German Center for Cosmological Lensing, and I'm presenting the CLMM Python library for cluster weak lensing mass modeling, which was developed by a large team for the LSST desk, many members of which are participating in this workshop and presenting work enabled by this code. So CLMM was envisioned to enable end-to-end validation on mock data of desk's cluster cosmology analysis pipeline before directly applying it to real Rubin data. Rather than being an end-to-end pipeline itself, it's a toolkit of modular pieces so that users can flexibly build coherent pipelines that propagate all assumptions. So for example, the cosmology used in unit conversions before a cosmology fit. So the code is developed publicly on GitHub and includes continuous integration, unit tests, thorough documentation, and a comprehensive suite of examples. So it's a robust code accessible to the broader community. So we hope you'll check out the poster and the paper on arXiv and of course the code. And if you're interested in joining and contributing to this community resource, please get in touch.
Thank you very much, Alex. Next talk from Marina. We already listened to you yesterday, but you have a poster this time.
Yes, hi. So I wanted to give a brief update about a project that aimed at studying low mass individual clusters at redshift of about approx 1 using a multi-wavelength approach. And for that, we map the internal structure of 3 XXL X-ray selected clusters with resolved SZ data coming from the Nikka 2 camera. So you see on the left, the first target we analyzed, and this is a composite image using optical millimeter and X-ray data. And so this guy appears to be like a bullet cluster, but at a higher redshift and lower mass. So we studied how this complex morphology impacts the mass measurement and thermodynamic profiles. So please check the paper or the poster for more information. And also we are analyzing the 2 other systems that are also detected by ACT. So please reach out if you're interested.
Thank you, Marina. Next talk from Gopika. Are you online?
Yeah, I'm online.
We hear you very, very weak. And
am I audible now?
it's a little bit better if you speak as loud as possible.
Yeah. So hello everyone, I am Gopika from IIT Hyderabad. I'm a PhD student. So here I am presenting our work a test of constancy of dark matter halo surface density in relaxed clusters and flows. For a whole class of galaxies, it was shown that this halo surface density is a constant over 15 orders of 2 magnitude, and we argued this to be a universal constant as though it was objected by a series of work by De Popello. So it procured us to check whether this argument holds up for galaxy clusters and flows. Hence, we investigated this using a group of cluster catalogs of about 70 groups and cluster catalog of about 17 and 12 objects respectively. And we find that for clusters, the halo surface density is of about an order of magnitude larger than that for galaxies, and the surface density of groups fall in between that of galaxies and clusters. And here you can see a plot between the surface density and the halo mass, which is in log space, and you can see the cluster data falling just below the group data. So basically, the dark matter halo surface density cannot be a universal constant, and it shows a slight positive correlation with the halo mass. This particular quantity is very interesting because it can be used as a good test of LCDM and other alternatives. For example, Bocquet in the 2020 used this theme for testing the validity of fuzzy dark matter. So that is all. Thank you.
Thank you. Thank you, Gopika. Next talk from David Turner on the XCS survey.
Yeah. Cheers. So I'm just going to very briefly present some relatively new results from the XMM cluster survey, which is run by Kathy Romer and Paul Giles. Basically, we've developed a new piece of software called XGA, which is meant to be a comprehensive X-ray analysis module for Python, specifically at the moment for XMM data. And we've used that to analyze some of the XMM cluster survey detected clusters. So we're a serendipitous survey. We've used SDSS data, and we're also working closely with the Dark Energy Survey to produce large samples of X-ray observed optically selected clusters. And so here we've got some preliminary new scaling relations with about 60 clusters between the hydrostatic mass in the R500 region and the temperature in the R500 region, and also the richness as measured by RedMapper for SDSS. This is just a subset of the SDSS sample at the moment, but we've also measured masses for the ACT-DR5 release and DES-Y3 RedMapper catalogs. And in total, we have around 300 hydrostatic masses at the moment, which is obviously a significant new sample. And hopefully we'll be publishing information on that relatively soon.
Thank you, David. Thank you very much. Next talk is from Wonky Lee.
Hi, can you hear me?
Yes, very well.
Okay, my name is Wonky Lee, and in this poster, I would like to share our recent simulation study on ABBA 115. The multi-wavelength image of ABBA 115 on the left is kind of puzzling because the X-ray tail that is known to form along the merger axis by ram pressure and the radio relic, which is known to be perpendicular to the merger axis, is currently observed to be parallel to each other. To understand this system, we reduce the complexity by using our accurate weak lensing mass measurement as initial conditions and simulated different collisions. We found that as the gravity works on ICM but not on the shocks, the off-axis collision makes the X-ray tail to rotate, whereas the shock that forms the radio relic stays perpendicular to the merger axis throughout the merger phase. Therefore, we suggest that radio relic act as a more reliable indicator of merger axis, and the ABBA 115 can be explained with a post-merger scenario on the right figure. Please check our poster for more details. Thank you.
Thank you very much. Next talk from Jeremy Sanders.
Hi, yeah, so I'm Jeremy Sanders. So MBProj2 and MBProj2D are Python codes for modeling the X-ray surface brightness profiles of galaxy clusters or their images. And they use forward modeling to model these the clusters. And you give a parametric description of 3D cluster profiles, and they predict the surface brightness profiles in multiple energy bands, allowing you to get sensitivity to spectral variation. And then you can fit your model and use MTMC to get the model uncertainties, also allowing the use of Bayesian priors. You can either use a temperature model to model the temperature profile of the cluster, or assume hydrostatic equilibrium, which allows you to get hydrostatic masses. So on the right-hand side, you can see an example cluster SPT, I think it's a midnight cluster, observed by Chandra around 1,500 counts. You can see the hydrostatic and non-hydrostatic fits to this cluster, showing the agreement. And with the 2D version, you can actually model multiple clusters simultaneously. And they're frameworks, and they're pretty extensible as well. So see these papers or these links to the GitHub and contact me if you're interested.
Thank you very much, Jeremy. And final poster, a flash talk from Emmanuel Artis.
Yes, can you hear me? So, hi everyone.
Yes.
So I'm Emmanuel Artis, I'm a postdoc at LPS in Grenoble. And I'm gonna tell you very quickly about PSZ2G91, which is a galaxy cluster approximately as z equals 0.8, which is very massive also, with the mass equals to 7 times 10 to the 14 solar masses. And if you look at the left of the slide, you see this cluster observed by Planck, and you see that it's totally unresolved. Now, if you look at the right side of the slide, you see two maps of the Nika-2 camera of the very same cluster in the black region. And you see that now you start to unveil the structures of the cluster, as well as the point sources. And if you look at the XMM Newton mass map, you also see the surface brightness map. You also see that there are two clusters, two subhalos. And of course, this has a huge impact on the cluster morphology. And in the work that I'd like to present you on this poster, you see how we go beyond the spherical assumption with this cluster to go beyond the spherical assumption. So if you want to know more about this, you can have a look at the poster.
Thank you very much. Thank you very much, Emmanuel, and all the speakers. So we're on time. Thank you. I think we can then continue with the next session, and I give the floor to Ben. You're chairing the next session.
Yes, thanks, Bruno. So now we're on to the topic of galaxy cluster masses derived from X-ray data, and we're going to have 3 talks on this topic. The first one is a review talk from Marguerite Pierre. So hopefully, Marguerite, you are with us and you can share your screen.
Yes, I am. I just need, can I share my screen while Bruno is still
yes, sorry. Yes. I have to
also
stop sharing. Yes.
Recording as well. Okay.
So as before the talks, well, the first